This meeting is being recorded.
Good morning, everyone. Welcome to the second day of the Moon Village Association Architecture Working Group workshop for 2021-2022. Let me remind everyone, if you're not speaking, to please mute your mics. In particular, Maria at Yushnoi, please mute your mic. I'm not sure she heard me there. I can do it for her. The miracles of Zoom. Okay. Okay, very good. Okay, very good. Okay, very good. Oh, we got one more. Excellent. So we got a very good group this morning again. So just again, good morning to this second day of the MVA Winter 2021-2022 Architecture Workshop. I'm going to just share screen for a moment. So yesterday, we had I think a very good introductory first day meeting with presentations from NASA, from CAST, from ESA, from the US, Japan, China, Europe, on topics ranging across in space, in particular lunar construction and fabrication, and ISRU. Today, we're going to be continuing our discussion with a keynote by Professor Yoshifumi Inetani, formerly of JAXA, who is the co-chair of the MVA Architecture Working Group, and a number of speakers, beginning with Alexander Belgic from Yuzhnoye Space Design Center, and continuing with both government and industry and academic speakers across a variety of important topics related to humanity's future on the moon. This is the second day of a three-day event. The third and final day will be tomorrow, and we'll continue the discussion on these topics and on others. With that, it's now 5:09, and we're just a few minutes early, but I think early is better than late. And so, if I may, let me turn the podium. I'll take a moment and turn on share screen. Okay, if I may, I will turn the podium over to Professor Inetani. Inetani Sensei, you have the floor. Please go into your keynote.
Okay, thank you, John. And thank you for the time for me to give you a talk about our activities. And yes, in the our groups are how do I say, doing building, let me say, village on the moon, or let me say the building society on the moon, and not only for the technical ones, but also for the non-technical things such as the business, the societal considerations, and the human aspect, and so on. And we have a study team in Japan, have a monthly gathering. And of course, due to this pandemic, and we have a web primarily web type gathering, but about 100 people are gathering every month. Then I will, today I will tell a little bit about what's going on in our activities. So can I share the screen?
Yes, you may.
Yep. How many minutes I have?
You have 45 minutes.
45?
Yep.
I didn't expect such a long, but it's okay. I'll try. This is okay. Can I see this? That's the top page.
It looks good.
Okay. And yes, this as I told you, that we are doing studies from the reference modeling. Reference modeling, which means to think about the village or society on the moon. Everybody has a different image of the village or society. So if we do discussion more, let me say, having a concrete image of this, and then the building a reference model would be good for us to think about what will be going on, what will be done for building it. So this is our background idea. And today, I will tell a little bit about the reference model study status. And in addition to that, some updates for transportation and life science kind of things a little bit. So that's my talk today. So the motivation to reference modeling is, as I told you already, there are many discussions for the creation of society on the moon, but with a mixture of realistic or non-realistic things mixed. In order to have make the village society happens, and we have to be, let me say, realistic, but we have to have, how do I say, the engineering, science way of doing things. And this kind of motivation for what reason we build society, or what should we discuss to build it, and is it economically viable, or how to solve to make these village into reality, things like that. So in order to do that, the building a reference model, and then have a concrete image on this village society would be a good way of doing things. That is the motivation to making a reference model. The reference model assumptions, this is also, there are many discussions on the way of doing things, but an assumption is, if we agreed upon these assumptions, the discussion should be in progress. That's our idea. So the assumptions, number of habitants, what they're doing, and under these conditions, building this ecosystem of the Hmong village and society. That's on our studies, the assumption is 1,000 habitants. And based on this number, to figure out the society infrastructure and supply chain networking. That's from architecture point of view. That's one of the assumptions. What is the role of habitants? There are also many discussions, and we have some options in the A, B, and C. And the 1,000 people are all workers, or to certain time period of stay, or workers and their family, including children, and the many years stay. The assumption C, the steady state society, which means we have not only for the workers and the parent children, all the people going to die and birth and things like that. That's let me say, the society. That's the population pyramid can be considered. This kind of thinking is possible or not. Of course, not for today or tomorrow, but in how many years it would take. But this is a thinking experiment. And what are the revenue sources? And the economical value system can stand for being sustainable in building this society. Now we have to be built or make or create the value on some activities on the moon. Then the economically viable system will be built. That's the idea. So that on that context, the revenue sources, which means what do we create in terms of value, is one of the important things. And two examples will be imagined easily. That's one is the resource utilization on the moon and mining it and selling it, for example. Another one is on the tourism. That's we assume that, for example, the 10,000 tourists every year from us and back, that would be the assumption. Can we take care of that? In order to do that, what kind of transportation systems, infrastructures, and living systems should be prepared? This kind of things will be quantified. And for building society, as I told you, then if we think about this long time sustainability, so we have to have birth on the moon, death on the moon, childbearing, education, and hospital, schools, and things like that should be prepared. The kind of things we can imagine. So this kind of scope of the business, or scope of our thinking experiment, that's our assumption. And then how do we cope with it? Is we have 5 working groups on this. One is the architecture working group. That's quite a similar activity John is leading and in the Moon Village Association. And the business working group, also we have an Oleg Ventkovsky in the Moon Village Association is also working on this business type of job. And the other one is a life science working group, regulatory issues working group. The regulatory working group is doing rule making, governance issues, how to operate a society and rule making, things like that. To think about these kind of things. And finally, the humanity, culture, anthropology issues working group. So that we have in each working group, one is 3 to 4, 2 in the larger groups, and 7, 8, 9 people are working on these work groups. What is important on this context is the relation or the interaction between these working groups is very much important. That is our thinking. For example, the business making and architecture are, of course, the technically possible, or the consideration for making business is important in such an interaction among these working groups are also very much important things. That's the last thing. So today I will, that's the way of doing things, and I do not tell everything about these activities, and the study is on the way, and yeah, and maybe approximately in every hopefully year. This and we will tell you the progress on this activity. So today I will tell you a little bit about the transportation and in the later part the life science kind of things. So first to talk something about the transportation. And if we do think about the 1,000 inhabitants, and those people are, of course, staying in it, but even we do maximum use of in situ resource utilization on the moon, but some amount of transportation is also, of course, necessary to keeping a good supply chain management. And in addition to that, if we assume that for the business making for tourism is our assumption was, as I told you, 10,000 tourists every year to and from the moon, in the Earth moon and transportation is necessary. So in order to do that, what kind of transportation architecture is needed? That's let me say the in between the Earth and Moon, we have to have let me say traffic networking. For example, the day one we launch, and 3 days later or 4 days later, it reaches to the moon. And if we do that every day, the next day we launch it. If we do these kind of things by present technical basis, such as an SLS for taking care of, which takes care of the Artemis programs, and to my knowledge, and one shot of SLS will cost more than $1 billion. So that means that if we do that every day, the first day, $1 billion, the second day, $1 billion, 5 days, 10 days, $10 billion, and maybe more. That will be not economically viable. So in order to do that, the transportation costs should be drastically reduced. Current activities by SpaceX, building Starship, they will take care of that, or much more frequent transportation architecture is needed, like an aircraft type operation of a very frequent transportation system. It should be built. There are many ideas and many way of doing things. Then in between the relation between the architecture working group and business working group, from this point of transportation point of view, it's 10,000 tourists every year, and what was it? Resource mining, processing businesses. That which means, and I would tell you in the later part, we need propellant production on the moon, selling it, and this is the business. Then the transportation system works. This is the business architecture relation. It is we can imagine. And then what kind of traffic networking is possible? And there are many ways of doing things, but on the ground to LEO and the cis-lunar orbit and lunar surface, there are 4 locations, and the fuel depot on orbit is there are several ways of doing things. And for thinking about the delta V in between, and then what is a good way of doing things. And in the later part, I will show you that the fuel depot in LEO from the Earth, of course, and fuel production on the lunar surface, and maybe some idea is in the cis-lunar orbit tank station, and or on the lunar surface. So there are several ways of doing things. But And anyway, this in order to have economically viable systems, and it is absolutely necessary to have fuel production on the moon. And then here, this and the part of ground and LEO will be in the transportation studies after the shuttle and discussions for the fully reusable space transportation system, which will be capable about 2 order of magnitude cost reduction. If we make these things happen, and then we do our assumption on this part is such kind of a very 2 order of magnitude cost reduction transportation system is made. Then the orbital transfer systems or landers will be prepared. That's our assumption. Then this one is the ground, in the transportation between ground and the LEO. We have a tourism and point-to-point transportation and things like that. We have a very large market, and then which will take care of a 2 order magnitude cost reduction. This kind of study is done by space tourism studies and the point-to-point transportation studies. And then they're taking a look at the LEO to the moon transportation. And if we do that in the everyday basis, for example, as I showed in the previous pictures, and first day we launch it from the Earth, then one day later it will come somewhere around here, but next day we do launch our next OTVs, and it will take more than 3 days, sure, 4 days from LEO to the lunar cislunar orbit and lunar landing, which means about 10 vehicles are going around like this in order to have a everyday flight basis on that. So what is the transportation capability? Is in the 10,000 passengers every year, which means if we do the everyday flight, it's on each flight we have 30 passengers by OTV on that. So then the OTV and landers, which is capable about carrying 30 passengers on each OTV capability is necessary. Then we can do sizing and vehicles and things like that, and how much fuel or propellant is necessary on that. We can figure these kind of things out. So we do that. This is a size comparison. It's if we do this OTV in such a way, 30 passengers to be carried, and 20. My sizing result will be sometimes very optimistic, but 20 ton dry weight and 30 tons propellant, which means a LOX LH2. So this fuel should be carried from the Earth to the LEO, and on the other hand, from the moon, that we have to have this amount of fuel we have to do every day. So 30 tons of propellant carried from the ground to the LEO, and on the other hand, 30 tons of fuel is produced and loaded onto this OTV landers. So every day we need 30 ton propellant on both sides. That's a very large numbers. So, but we can be optimistic about that. So how many fuels every year will be an annual production is figured out by this assumption. And the size comparison is this one is of course the Starship lunar landing part. And this one is in the Blue Origin national team, and this one is a little bit different shape these days, to my knowledge. So anyway, that kind of sizing and quantification. So our interest should be done by what we'd like to know is what is the flight ticket price on this flight. As that's the we do not keep in touch with every detail on that, but this one is a cost breakdown of each flight. It's something like this. So if we do the fuel production on the moon, assuming that, then making some assumption presented here, that's we can be able to figure out that 30 million US dollar per flight. It's $1 million US dollar per person because the number of passengers is 30. So that will be the ticket price. That's a $1 million ticket price is possible under the condition that 2 order of magnitude cost reduction from the ground to the earth, and the lunar fuel production is down in this figure, like here, this one is written down. So the major portion should be this lunar surface price of the fuel will be the major part, and the other parts are minor parts, a portion, which means lunar propellant production cost is the key driver for determining the ticket price. That's our result. So 1 million ticket price, $1 million US dollar ticket price is I do not know is it possible or not, but under the assumption that this consideration will give us this result. Maybe the more than 2 order of magnitude cost reduction from the present transportation capability, such as based on the SLS and starships and such kind of things. So that will be becomes a future goal. So how many people are capable about can afford it? That's the market type of discussion will be started from this consideration. That's one thing. Another topic now is how many minutes? Yes, is in the progress in the life science working group is doing is the second topic of my presentation. And the life science working group is thinking about the to stay or the sustainable stay on the moon. What kind of life science consideration is needed? And of course, everybody knows that radiation hazard and low gravity impact to the human body would be the ones of the most important things, and they are thinking about these kind of things. So these two things are not very new things, but it is very important on that. But then we are now talking, which means we are now talking about the life science people or the little bit, how do I say, the consideration beyond this kind of radiation hazard and low gravity effect impact to the human body. It's this one is beyond life science consideration, which means if we do that a longer time stay, so the bearing and succeeding generations in space or on the moon or in orbit or whatever. The environment is very much different, as I told you. So those guys, those who was grown up on the moon or in space, can come back to the Earth, or in order to do that, they do the same life. They do the making the same life on the Earth, or did they adapt themselves into the environment down there. That's the choice of that. In the future consideration, for example, there's those who was born on the moon, grown up on the moon, can come back to the Earth. Is it possible or not? This kind of thinking could be made. So in order to do that, the sustainable human presence, the long time period, is an idea of a technical augmentation or enhancement of human capability. That would be the bioscience or bioengineering, making use of this bioengineering science knowledge. That will be possible. So of course, we have to have a humanity related considerations on these kind of topics, of course. But for a longer time period, an adaptation to the environment down there should be, we will be maybe confronting these kind of topics, maybe. Then the further thinking about that is a much longer time period for the time period of the human evolution time period. That's a million years. That's a far away from that. But thinking about this and the Darwinian evolution from now on will take place or happen, or much more technical countermeasures to do that. And in some science fiction, people say that the post-human or quicker evolution will be possible, making use of these bioengineering enhancement or the augmentation technology and things like that. So this kind of topics, to my how do I say, curiosity, and this kind of topic is, to my view, it is very much interesting for me. But this is not a topic of an architecture point of view today, tomorrow, or within 10 years, 100 years, but you know, we if we think much a longer time period, that we will be confronting these kind of topics or problems. So that's I just tell you our life science people, and we are talking about what kind of consideration will be very interesting on this context. So the new discussion underway, that one thing, as I told you already, is in transportation architecture for 10,000 passengers every year to and from the moon. It's very much different world than today. But in order to make this kind of things happen, so we have to have this kind of fuel depot and production on the moon, and very low cost supply on these propulsion fuels and oxidizers on the moon will make these figures into reality. It's the $1 million flight ticket possible under the condition that these kind of fuel supply becomes a reality. That's one thing. And life science people, and we are thinking about much longer time sustainability of a human presence in space, on the moon, in orbit, or somewhere in a different environment than the Earth would be an idea of an augmentation or enhancement discussion, making use of bioengineering or let me say the post-human type of technology would be one of the interesting topic to my view. Okay, so in such a way that many new and diverse thoughts are underway in the reference model studies. I myself is wishing to do this. I like myself like to do this kind of discussion. Very much interesting. Okay, that's all my presentation. Thanks, everybody. Thanks, John.
Thank you, Inatani Sensei.
Yep.
I certainly feel that I'm being too conservative in all of my thinking. Although usually I am not accused of being too conservative. So we have time for one or two questions. If anyone has any questions they would like to ask Inatani Sensei, I assume that's okay.
Yep.
So I will start. I would just make a suggestion. I think with regard to the cost of propellant on the Earth.
Yeah.
I am while you were speaking, I was looking at the major components being, of course, for green hydrogen, being electrolysis and liquefaction.
Mm-hmm.
And maybe it would be useful to sort of turn the problem around and look at the cost in kilowatt hours
Mm-hmm.
per load of propellant to take the 30 people to the moon, rather than dollars. So rather than $2,000 per ton, so many kilowatt hours per ton.
Yeah.
And then you can determine how cheap does electricity on the Earth need to be to reach $2,000 per ton.
Yeah, I didn't show this breakdown and how what is the way of production and how much on electrical power we need. It's it is important. I admit it, and then it's quite interesting consideration and how much the production cost we have to have and how much power we need and things like that, both from the Earth to carry it to the LEO and production on the lunar surface cost.
Yeah.
Our hydrogen people maybe yesterday or maybe today or tomorrow we have a hydrogen society people are thinking about these kind of things, and we will be working together with this and the resource utilization people and to figure out these kind of energy and cost and the production cost and things like that. This kind of consideration. We would like to continue this kind of calculation and consideration. Thank you very much.
Yeah,
it's quite important.
And it becomes the if you calculate everything in terms of kilowatt hours, i.e. the megajoules or gigajoules, as opposed to dollars, then this will not change.
Yeah. Okay.
Dollars and euros go up and down, but 100 years from now, the energy will be the same.
Energy is a much more universal unit, you mean?
That's my thought.
Yeah, okay. Thank you very much indeed. But money is very much familiar for everybody.
No, I know. It's very useful for a general discussion, but in terms of the calculation.
Okay. I admit it. Thank you very much.
Okay. Any other questions or comments for Initani Sensei? Okay, if the answer is no, it appears to be no, then let's, if I may say, thank you very much, Initani.
Yes,
great.
thank you very much. And our thinking is becomes diverse, and somebody stop me.
It's excellent. It's excellent.
Okay.
So if you would please stop the screen share.
Yeah. Stop it. It's okay.
Very good. Very good.
Okay, thank you.
Thank you so much. Our next presentation should be from Alexander Berdik from Yushnoy's State Design Bureau Office. Are you available, Dr. Berdik?
Yes, we're here.
Oh, there you are. Excellent.
Hello.
Good day for all.
A very early good morning from California.
Thank you.
And this is good day from Ukraine.
So we are almost on time. We're just a little behind because of the late start. But please, if you could give your presentation in about 20 minutes, that would be wonderful.
In 20 minutes?
Yeah, 20 minutes.
Okay,
You could take less time if you like, but
all right.
you can take if you take a little more time, we will make it up, so it'll be okay. But please. Can you go to full screen, maybe?
Yes.
Весь экран он спрашивает, можно сделать?
Yes. Я же не вижу.
А может нам, чтобы там кусочек остался? Do you see our presentation?
We can see it okay, but I was just asking if it's possible to go to full screen. The image is a little small. But there's a button in the lower right that looks like a projector screen. Nope, now we have lost it.
Just a second, we're trying to adjust it.
Okay, we have the image again.
Is it okay?
It's okay. Please go ahead. Please go ahead.
No way.
My presentation is auxiliary rocket transport for lunar activities. In 2021, within the framework of MVA architectural concept and consideration working group, Yuzhny SDO subgroup studies prospective types of auxiliary lunar rocket transport. The aim was to further safety of manned space flights during the rotation of lunar base crews and other human external moon activities, expansion of mobility and efficiency, as well as increase of load carrying capacity of lunar rocket vehicles. The following subjects were considered: Moon Emergency Rescue System, MERS, for the manned lunar lander crew, Universal Moon Flyer for rescue missions or urgent delivery of personnel and cargo to the required region of the moon surface.
Please excuse me, are you still on the title slide or do you mean to advance the slide?
No, we have advanced to the slide number 2.
It has not changed.
Не изменился слайд. What about now?
Not
Has
yet,
it changed?
not yet.
Нет.
Нет. Two.
Это у парня что-то не работает.
Okay, now
And
it's the
how-
second slide. Very good.
Okay, thank you.
Okay. Universal Moon Flyer for rescue missions of urgent delivery of personnel and cargo to the required region of the moon surface. Integrated lander Skycar aim for heavy and bulky freight transportation. These types of rocket transport are better to put into operation after beginning of the reusable lunar lander regular operation, which considered early in the materials of lunar base development concept.
След-
Next. Далеко. Developing of the moon emergency rescue system for the manned lunar lander crew, the aim was to enhance the reliability and safety of the manned missions for the lunar base, in particular, safety of crews in the circumlunar orbit, lunar base transfer and return. After the analysis of flight conditions, it was decided to select a version of compact and lightweight system, which will rescue the crew if the lunar lander fails in any flight stage from the circumlunar orbit to the lunar base, as well as on the way back. For the minimized impact of the system on the manned lander capabilities, the concept is based on the following principles. The rescue is ensured in any trajectory segment, crew rescue in space suites without pressurized cabin, rescue of all crew by one device or person system is considered. Safe transportation of crew to the circumlunar orbit near the station or the lunar surface. Minimum mass and overall dimensions. Minimum time between the command and emergency space of the lander. Next.
след-
Не работает.
следующий.
MERS application scheme is as follows. In case of failure on board the lander during the circumlunar orbit lunar base flight, the crew escaped the lander on board the MERS. Following the situation analysis, one of system algorithms will be selected. 1. Emergency return to lunar orbit, or 2. Completion landing on the lunar base. For the case 2, is necessary to equip the lunar base with the recovery vehicle for return to the circumlunar orbit, or have enough resource to wait for the rescue lander arrival.
Следующий.
Подожди, вот этот вот. During the circumlunar base lunar orbit flight, there will be 3 options of emergency trajectories. Depend on the current velocity and altitude. After the separation from the payload lander, MERS can perform the following. First, return to the land point, lunar base. Return to the launch point, lunar base. Second, emergency landing on the moon in the emergency landing point. Third, completion of the orbit injection. There is an universal moon flare and the emergency landing site. Moon flare will be referred to after. This delivers the crew to the circumlunar orbit to continue the mission. Application of such a rescue approach provided the minimal MERS capabilities requirements. In particular, for its propulsion system, it's a notch to gain delta V of 1100 ms meter per second, and this essentially reduced mass of the rescue system.
So,
Main characteristic of the MIRS. As is obvious from the figure, emergency rescue system for the crew of the moon lander is the rocket vehicle equipped with seat liners for astronauts in spacesuits, liquid propulsion system, landing system with 4 landing legs, and avionics unit. In particular, systems of control, navigation, and communication. Vehicle main engine operated according to the simple and reliably pressure-fed schema and use hyperbolic propellants from the embolized tanks. Altitude control system microthrusters are powered by compressed gas oxygen of the common pressurized bottle. This bottle can also be used for refueling of spacesuits. Table show basic MIRS characteristics. Initial estimation. As is obvious from the table, its mass does not lead to an essential decrease of the lander payload capacity, because mass of the system is 29% less than mass of the crew in spacesuits. The main cabin upper part will need to be modified to make it openable for the quick escape of pilot lander when using the MERS.
so
As the second type of auxiliary lunar transport, the small universal lander, Moonflyer, was considered. It capable of performing of the following functions. 1. Emergency transfer to the crew from the lunar base to the circumlunar orbit in case of emergency or failure on the main manned lander. Second, emergency aid or evacuation of the crew members working at the remote distance from the lunar base, if it's impossible to get help by the soil transport, surface transport. Third part, transport of people and cargo to the remote orbit of the lunar infrastructure, urgent repairs, etc. Next, there are a list of vehicle requirements including a capability of use the lunar propellant. Universal moon flare can be developed on the basis of the heavy lunar lander developed nowadays in Yuzhny SDO. It's powered by the liquid propulsion system using the hyperbolic propellants. The vehicle is equipped with power unit on the basis of the 3 single-chamber LPA landing system with 4 legs, avionics, in particular control, navigation, and communication system. The payload is installed on the upper platform, CDPG. If crew in space seat are to be transferred, then seat, manual control panel, and radiation and micrometeorites shield will be installed on top. For cargo's delivery mission, top platform will be equipped attachment for cargo bringing and unloading.
Следует.
As seen from the table, with mass about 2.3 tons without cargo, Moonflyer can provide emergency transfer of crew to the circumlunar orbit or flights across the moon at the range up to 330 kilometers, with returning to the base of more than 500 kilometers in one direction. When production of lunar propellants is at hand, such Moonflyer will be powered by the moon-produced propellants, hydrogen peroxide and hydrocarbon fuel. 90 of raw materials for these propellants can be obtained for the lunar water, and just 10% carbon can be either brought from the Earth or extract from the lunar carbon dioxide deposits, which are expected to be found in lunar rocks at the same time with water ice extraction. This propellant is considerably expand of the universal Moonflyer wishing for the local transportation. Hyperbolic propellants is easy to store for the long time. Besides, it's important this mix using for its production, but less hydrogen, which is more valuable on the moon than oxygen. One more kind of auxiliary lunar transport is the integrated lander sky crane.
Следует.
Extraction of lunar rocks may require delivery of heavy or bulky equipment to the areas where landing of cargo landers is hazardous or impossible. Slopes, canyons, lava tubes. Besides, a return of this equipment may be also required for repairs and recovery. The integrated lander will solve this task. Among such cargoes are mining machine, robo-miner, row harvester, nuclear reactor of small power station, other large infrastructural objects which have been assembled at the lunar base but will be applied away from. The idea is to use several standard reusable lunar landers integrated into the common structure, as is shown in the figure.
Следует. Назад. Вот это.
Integrated lander is structurally as X-shaped for beam platform, where payload is suspended under the center of mass using the rope system with engines installed away from it. To minimize the expenses, the heavy landers is developed from the 4 reusable lunar landers, RLL, involved in regular delivery of cargoes and crew to the lunar base and installed at the ends of the beams. System of float attachment with winch is installed in the central parts of the platform. General control system units and other avionics are also installed here. Central part of the integrated lander is delivered to the moon in one folded piece, then is get unfolded and assembled by making 4 RLLs, which arrive with other missiles. Next. The maximum cargo lifted by the vehicle will be determined from capabilities of RLL engines and from necessary thrust margins determined by safety requirements. The basic mode of transportation and unloading with horizontal movements at some altitude over the lunar surface and hovering on the vehicle over a place of delivery with steady operation of the major parts of engines is assumed. It improves reliability of operation, such as resulting in increase of propellant consumptions. Preliminary estimate of the lander sky crane of them on the basis of 4 RLLs showed the capability of handling cargoes up to 135 tons and flying with a cargo a distance of up to 104 kilometers. Next. Integrated similar, if required, similar integrated lander can be assembled from the different numbers of RLLs. For example, 3 or from 3 to 6, 8. Thus, the concept of integrated lander on the basis of standard RLLs will allow handling of more massive and dimension structures, delivering them to the site inaccessible to other transport, and if necessary, to return them to the main base for various complex activities. This will expand the accessible area for complex equipment, which will accelerate the implementation of ISRU technologies and development of lunar infrastructure with no need to develop more heavy launch vehicles for lunar activities. Thank you for your attention.
Okay, thank you so much. A very interesting set of new concepts.
Очень интересно. Новые концепты.
We're running a little bit behind, so we don't really have time for much discussion at the moment. I will just pose, if I may, a challenge. So at least in our studies, one of the zones for the design reference case study is an unmanned but human-tended science station on the far side of the moon. It would be very interesting if you could look at what a vehicle might look like to take personnel, for example, repair and maintenance personnel from the main settlement at the South Pole to, as a hopper, to a science station on the backside, and then to bring those people back after they have done their servicing of the observatory.
Говорит, что как в качестве такого челленджа было бы неплохо, если бы там есть какая-то научная станция на Южном полюсе. И вот было бы неплохо рассмотреть вариант, как можно придумать такой вот аппарат, который бы мог туда слетать, например, там провести какие-то ремонтные работы или людей привести, а потом на другую сторону, а потом вернуться в основное поселение. Вот чтобы вы рассмотрели, какие есть возможности, вот какой можно придумать аппарат, чтобы обслуживать вот эту вот научную станцию и возить людей туда-обратно для каких-нибудь ремонтных работ.
Я могу сказать, что вот если дистанция если станция находится в пределах 200 километров от основного поселения,
Мгм.
можно использовать рассмотренный в данной презентации Universal Multiplier. Если будет большая дистанция, можно будет использовать RLL, который был показан в моей предыдущей презентации год назад.
So his answer is if the distance is around 200 kilometers, then you can use the universal moon flyer that he presented in his presentation. And if distance is bigger and longer to cover, then you can use the RLL vehicle, which was shown in the previous presentation before.
One a year.
A year ago, yes, presentation
Yeah,
a
yeah.
year ago. Mhm. So
Okay.
that's his prompt answer.
So it's really.
So it's really realistic challenge to tackle.
Okay, very good. So thank you so much. Could you stop screen sharing, please? Oh, very good. Thank you. And our next presentation is continuing in the theme of infrastructure and transportation, is from Dallas Bienhoff. Dallas, are you ready to go?
I am here, John.
Wonderful. Thank you for your patience. Please don't cut your talk short. Go ahead and you have the floor.
Okay, thank you.
And please say a few words of introduction about yourself and your activity.
I will do that. Why don't I find share? Oh, staring me in the face. So I'm Dallas Bienhoff. I'm a founder of Lunar Space Development Company, and we are developing transportation concepts, architectures from low Earth orbit to the moon, reusable using LOX hydrogen. There we go. It's all good, John? John, can you hear me?
Oh, sorry, I was on mute. Yeah, looks
Okay.
great. Please go ahead.
Great, thank you. So last year I was talking with the space portal at NASA Ames and on one of their telecons and said, is SpaceX Starship really a panacea for all missions? And I did a comparison of cost, not price, cost of several architectures getting around in cislunar space. And for today, I've simplified that and reduced it to just looking at the comparison for going to the moon. I have, excuse me. I have to say that all of the information relative to the NASA human landing systems from Blue Origin and Dynetics are my numbers estimated based on what was available publicly. These are not those companies' numbers, so they're estimates. The Starship, same, it's from Wikipedia, and so bear in mind this is my data. It's not official from anybody, and this is cost, not price comparison. So I'm going to talk about the architectures. I'll explain the architectures that I'm preparing, talk about their maximum capabilities, some basic assumptions that went into the assessment, look at cargo delivery to the moon and people delivery to the moon, and do a summary. And then behind that, John, for your reference, is some supporting data that I will not go into today. So the first architecture is the Gateway, the SLS Gateway Blue Origin human landing system. The crew gets transported to the Gateway on Orion. The Blue Moon lander is based at the Gateway in the near rectilinear halo orbit, and it gets refueled from a CSDC depot at the Gateway. We did a study for Blue Origin on our own dime, coordinating with Blue Origin or Blue to look at what it might cost them to buy propellant from CSDC. So that's the basis of this assessment. The second architecture is again, the SLS Orion Gateway and Dynetics human landing system, the Alpaca, they use LOX methane, and they also buy propellant from CSDC. And again, we did an internal study for them in coordination with them on what it might cost them to buy propellant from CSDC for their human landing system. And of course, we can't forget the SpaceX Starship with the Gateway and SLS Orion. And they deliver their own propellant to the moon with their Starship transfer vehicle and reuse it. Then there's the Starship only architecture. Uses the Starship and heavy booster to get to orbit, a transfer Starship to get to the moon, depot Starships in low Earth orbit and the Gateway near rectilinear halo orbit, and then a lunar lander that stays there and carries people and or cargo up and down to the moon. And then there's the Cislunar Space Development Company's architecture. We have reusable space tugs from from low Earth orbit to the Earth Moon L1 point. We have propellant depots in low Earth orbit and at Earth Moon L1. We use Moon Shuttle to get up and down to the moon. We have a personnel module that is carried by the
Dallas, can you hear me?
He must be muted, John, or he's lost his connection.
Gary, can you hear me?
I can hear you fine. His
Okay.
screen is frozen.
Yep, I was just
he has no
noticing
audio.
that. I was worried it was me.
Yeah, he's lost his connection. He's dropped now.
Since he's here in the US, I can give him a call. Or at least I can try.
Hi, this is Dallas at Cislunar.
Okay, John, it looks like I'm back.
Okay, very good. Welcome back, Dallas.
So I just finished up describing the Cislunar Space Development Architecture. Did you get all of that?
For the most part, yes. You might want to
Okay.
go back to share screen again.
I will. Yes, thank you. And there we go. Okay. So some basic assumptions. I assume that the SLS Block 2 mission cost was $500 million, whether that's carrying an Orion or cargo. And this is quite low compared to the NASA's Office of the Inspector General that said that the mission cost could be as high as $4.1 billion. So keep that in mind. I assumed a Starship launch price of 100 million on the high end and 10 million on the low end. Some internal assessments indicate that the cost of propellant is on the order of 2 million, but what the price is, nobody would know. But this is the cost to get 100 tons or 100 people up to low Earth orbit. I assume the same launch price, $100 million for the Blue Origin New Glenn and the Vulcan Centaur. Our depots, the CSDC depots in low Earth orbit and Earth Moon L1, add $500 per kilogram to the cost of propellant because we deliver water to those and then process them. So that's the cost of operating those systems. Crew Dragon and Starliner seat price comes from an article in 2019 on space.com. That's 90 million and 56 million. I assumed 1,000 kilograms per person for Starship, so 100 people is 100 tons. Blue Origin, Dynetics, and CSDC assumption is 400 kilograms per person because basically they need to bring themselves and a spacesuit. Most of the ancillary equipment is a fixed number for those vehicles. CSDC sells propellant to Blue Origin and Dynetics at the Gateway near rectilinear halo orbit. And these are steady state assessments with all assets in place. So we're looking at kind of what it might take in the 2045 timeframe for the Oasis concept. So what are the maximum capabilities of these architectures? So for SLS Orion and the Human Landing System, the maximum capability to low Earth orbit, the SLS can put 130 tons into low Earth orbit or 4 people on Orion. That blue bar is the cargo mass, and the burgundy brown bar is the number of people. To Gateway near rectilinear halo orbit, the SLS can put 40 tons, and to the moon with the Human Landing System being the Starship can put up to 40 tons on the surface. And 4 people, because that's all that gets out to the Gateway on Orion. The Starship, note the change in scale, goes from 140 to 1,000. The Starship can put 100 tons or 100 people into low Earth orbit. Its maximum capability to the Gateway is about 550 tons or 100 people, and its maximum capability to the surface is over 800 tons and returning empty, or 100 people. This maximum capability is when the tanks are fully fueled with 1,200 tons of propellant and operating with a full tank load from low Earth orbit to the Gateway has a huge impact on the cost of or the value of propellant and cargo in the Gateway. And then CSDC on the New Glenn or Vulcan, the New Glenn puts 45 tons in the low Earth orbit, or 6 people on one of the commercial crew vehicles from SpaceX, that'd be the Crew Dragon or Boeing Starship. We could put about 30 tons to Earth Moon L1 or 6 people, and we could put, let's see if I can minimize this, about 65 tons on the surface from the Gateway, from Earth Moon L1, and 6 people. Our personnel module is designed for 6 people round trip from low Earth orbit to the moon. So looking a little closer at each of the architectures at the Artemis Blue Moon architecture, again, the LEO cargo on SLS is 130 tons. Cargo to the moon, if SLS were used to put cargo at the moon, it's 40 tons. And then the Blue Origin can put about 8 tons down on the surface as a cargo, because that's the mass assumed as the ascent vehicle. People to the moon is 4. There's a minimum propellant number that the Blue Moon would need to operate between the Gateway and the surface of the moon, and that's about 5 tons. Propellant to get cargo to the moon is 20 tons, and propellant to get people to the moon is 30 tons. So it would take several trips to get 2 trips to get the 40 tons down to the moon from that an SLS could deliver. For the Alpaca, that's the Dynetics. The Earth to orbit capability is the same, and the cargo to the moon or to Gateway is the same, and the number of people. Dynetics can put 20 tons down to the surface of the moon. People again is 4. Minimum propellant is a little higher because it is a reusable lander with drop tanks. So it's about 8 tons. Propellant for cargo and people is the same because we maximize the cargo by using all of the drop tanks. So that's about 30 tons down to the surface for cargo and for people. The Artemis Starship architecture, low Earth orbit is again 130 tons and cargo to the moon is 40 tons. People to the moon, again, only 4 because that's what Orion can get there. But look at the minimum propellant required to get to the moon, 350 plus tons minimum. To put the 40 tons on the surface of the moon takes another 40 tons, and put people on the moon, the 4 people, is again about 350 tons because the Starship is such a massive vehicle, 120 tons. And this is what drove me to question whether Starship is really a good vehicle for missions like this because of the massive inert mass, the large inert mass of the vehicle. For SpaceX Starship, a little more complicated. On the left is what super heavy Starship can put to low Earth orbit, 100 people, 100 tons. In the blue and the orange of propellant, it could put 100 tons of propellant to orbit. It could put 100 people to orbit. The gray, the yellowish color column is a payload volume. I calculated this from the user's guide and that SpaceX has put out, about 650 cubic meters. I've seen as much as 1,100, but I could not get that even with the expanded payload volume. It has 1,200 tons of propellant capacity. The depot Starships, if the payload volume is the same, is used as propellant tanks as well. I calculate it can hold up to 1,800 tons of propellant. That's LOX methane as a depot. The transfer Starship, again, it has a cargo capacity of about 550 tons, propellant the same, delivered to the gateway. The gray, 100 people. The yellow payload volume is a constant. The propellant volume inside Starship or mass inside the Starship capacity is the same, 1,200 tons. The minimum mission propellant to the gateway and back is about 250 tons. The max payload, again, about 550 tons. The max people, 100. And the propellant to get the people back and forth is a little over 400 tons. When we do that with a full propellant load, then we could deliver propellant along with people to the gateway. For the Lunar Starship, the constants are still there, the 100 people, the 100 the payload volume and the propellant capacity. The minimum mission propellant, a little under 400 tons. The maximum payload, a little over 800 tons. And the number of people to the moon, 100, and the number of the propellant for people, about 650 tons. So again, it is a huge vehicle with a great capacity, and its benefit comes from operating at this full capacity, not at the minimum number. If we're only carrying 4 people down, then it's really not a good deal. For CSDC, the Vulcan Centaur could put 45 tons to low Earth orbit, or 36 tons of propellant. I assumed an 80% propellant fraction for propellant tanks in the payload volume, or 6 people. The Vulcan is 27 tons. The New Glenn is 45 tons, and propellant is 36 tons. The Starship, if the Starship is the first leg to low Earth orbit, then it's 100 people, 100 tons of cargo, or 80 tons of propellant. And then down to the surface of the moon, to Earth Moon L1 rather, 6 people, 20 tons of minimum propellant, over 60 tons of propellant capacity. Propellant for people takes about 45 tons. Max payload is a little over 30 tons, and propellant prop delivered is about 30 tons. Down to the moon from Earth Moon L1, we can you get about 50 tons of propellant. We can put it has about 90-ton propellant capacity. It uses about 80 tons for carrying the personnel module round trip, and its max payload is about 65 tons. And we don't deliver propellant down to the lunar surface. So what does this? What does all this mean? The spaceship, the Starship, SpaceX Starship architecture cost per kilogram to the lunar surface is 5 to 16% of that of other architectures using maximum capabilities. And these columns show the various architectures. The Artemis Blue Moon on the left, using the low Starship cost of propellant, or the high cost, the 110 tons versus, or 10 million versus 100 million per launch of the Starship to get propellant out to the moon. So the blue is the cost to low Earth orbit. The gray is the cost from the lunar vicinity down to the moon, whether that's the gateway or Earth Moon L1. And the orange is a cost from low Earth orbit to the lunar vicinity. And you can see in the, you can see my cursor, the Starship. I looked at both the 100-ton capacity or 100 people capacity, 100-ton capacity, or the full capacity, and the difference there is considerable. And at about 50% capability, the SpaceX Starship at 100 tons would be equivalent to the CSDC using the low propellant cost. On the cargo side, 50 tons versus 100 tons, and it would be about the same as the other architectures on the high end. So full capacity is the key to the Starship being such a bargain to the moon. And for people, again, here it's even more dramatic. The Starship per person at full capacity is 0.5% to 2.5% of the cost of other architectures per person getting to the moon. Even at 1 or 2 people, if a factor of 50 brings it up to the cost of these other architectures. And I was surprised by this ratio, but that's the cost. Who knows what the price will be? You know, the price could easily be equivalent to all the other architectures, just by setting the price and reaping more profit. So I did not attempt to ascertain what one's profit might be. These numbers also do not include the amortization of the vehicles or the operating costs for mission ops, et cetera. So there's more to it, but the relative cost should stay up in the same ballpark. So in conclusion, nothing really compares to the Starship capabilities, and its best approach is to use it to full capacity, 800 tons, 400 tons, and not just the 100 tons or less. CSDC may offer the lowest cost per person to the moon for 6 or fewer people. SpaceX Starship offers the lowest cost for lunar access across the board at full capacity. And propellant cost in LEO is the major results driver of this assessment. What does it cost to get propellant to orbit. And launch and operations cost assumptions do drive the results of this assessment. So these are the architectures that I looked at. Surprising results from my perspective, and it's amazing the capacity and the capabilities of the Starship to go beyond low Earth orbit out to the moon. When I looked at it for Space Portal in comparison for geo missions, it does not fare so well, but for the moon, it's a great workhorse and can really reduce our cost of getting to the moon. Who knows what the price will be? And with that, John, I will close and turn it back to you.
Okay, thank you, Dallas.
And all I need to do is stop sharing.
Yes, please. So from the standpoint of our dialogue today, and I know we're running way behind time. We're gonna make it up at the break. We don't have a lot of time for questions or discussion right now. In fact, we have negative time. But I did want to just pose one question to you. So you saw the presentation from Inatani Sensei a few moments ago about the scenario for a large-scale presence on the moon. And I'm just curious, how do those assumptions line up with your analysis of the cost for Starship at full capacity?
Well, I have to admit, John, I did not set my alarm this morning and I barely made it on time for my presentation. So I missed his presentation. I'll have to look at the recordings.
Okay, very good. Well, let me have posed you the question.
Yeah. The Starship is the only way to support something like this. SLS is a 1-a-year vehicle. CSDC's architecture assumed once a quarter, and 6 tons and 25 tons, even for the Starship, is not, or the CSDC architecture is not going to support a large community on the moon. There's going to be the need for monthly high mass, high people count to support a community on the moon.
Well, I can give you the punchline, not taking into account the mass numbers. I think if I'm remembering correctly, Inatani Sensei's number was like $1 million per ticket to go to the moon.
Well, the Starship with the $10 million launch price is about $780,000
per person.
So at full capacity.
Yeah, so that's those numbers are not inconsistent. Is the key point? Okay,
that's
cool.
Correct.
Anyway, when you have a chance to look at the presentations in a week or two, you might take a further look at it.
I will do that. That'll also help our Moon Village lunar commerce workshop.
If I could turn now to Chiyoda Corporation, Shinohara-san, are you available?
Yes. Hello. Can you hear me?
I can hear you very well. You might turn your camera screen down just a little bit. We're looking at the top of your head. There you go. Thank you.
Okay. Hello, Johnson, and hello, everyone. I am Mutsumu Nagase of Chiyoda Corporation. And in this office, my colleague, Mayuko Shinohara, is also here from Yokohama, Japan. And first of all, I'd like to thank you very much to Inatani Sensei and all people here for giving us the great chance for attend this workshop. And if it's okay, we'd like to share the screen. Is it okay?
Please go ahead. Please go ahead.
So, Shinohara-san, please go ahead.
Okay.
Actually, okay, go ahead.
Can you guys see the PowerPoint?
Not yet.
Let's see.
You do have permission to share screen.
Okay. How about now?
It's coming now. Okay, we have it.
Okay, cool. Hello, everyone. Thank you for coming to this presentation, and thank you for inviting us to this meeting. My name is Mayuko Shinohara, and I'm from Kyoto Corporation in Japan. Today, I'm going to present the exploration service concept that leads to lunar water utilization. First of all, let me introduce our company briefly. Our company is our engineering company, which works in several engineering industry. Our main business is in plant engineering industry with hydrocarbon, LNG, and hydrogen. We also work in medical, biochemical industry, and also space industry. In past years, we developed some equipment that are used in International Space Station, such as a telecommunication system, image data transmission system, and life science system. Now we have been working on the project related to space. For instance, we have been in the project called Reiwa, which is under the contract of JAXA. This project is for developing the water extraction system on the moon for scientific research purpose. Although the research and development on the lunar water is already going on, we believe that lunar water can be used not only for scientific purpose, but also for industrial and commercial purposes. Now we are focusing on building method and technology to extract water from lunar regolith and how to utilize it for industrial and commercial purpose. Now let me explain the prospect of the lunar water utilization. So why do we want water on the moon at the first place? There is two answers to this question. One, water can be a clue of the origin of the moon and universe. And if there is water and sustainable human life on the moon, it is possible to bring scientists to their research and experiment in the condition where we cannot obtain on the Earth. Two, water is not only for scientific purpose, but also for building a human society on the moon. The reason why we want to do that is because, like I mentioned earlier, we can bring scientists for their research, and also it can be one of the leisure places for us in the future. And now let me explain how the water contributes to build a society on the moon. First, water can be used as rocket fuel. This is one of the most important reasons of extracting water, because if we can make fuel on the moon, we don't need to put extra fuel to come back to the Earth. It creates more space in the rocket, and it reduces the cost of rocket launch since the rockets will be lighter and smaller. Second, water can be a source of electricity. We can separate water into hydrogen and oxygen and build a hydrogen power plant to generate electricity. Third, water can be used for human living. In the future, we are planning to bring people for research or leisure purpose. To allow more people to stay on the moon, we will need water for drinking, hygiene, agriculture, and industrial purpose. This is a simplified flowchart of water extraction facilities. Based on this flowchart, we need to determine what kind of facilities we need to build or how big they need to be. To make those facilities, we need to make plans to explore the moon to do more research about the moon and the lunar regolith. It is really important to know the location, form, and the location, form, and the amount of water in regolith in order to build those facilities. I'm going to talk about the future plans for building human society on the moon, the exploration project, and the experiment we have done so far. This is one of the plans that were considered in 2021. Basically, around 2025, we will start the exploration on the moon to find out the resources that can be used for future facilities. We assume that it is better to send automated robots instead of sending people during 2020 for technical and safety reasons. By the end of 2029, you want to finish building a map which indicates the location of water, as well as the prototype of water for water extraction. In 2030s, we will start to build the water extraction facilities and the places where about 100 people can live. Once the facilities are built and proven that it is safe to go there, we can send scientists for their research and the people who want to go there for leisure purpose. In 2040s, we assume that about 1,000 people or possibly more people will go to the moon for research, leisure, or deep space exploration. If more people will go there, more facilities will be needed. Therefore, in 2040s, we will focus on expanding the facilities as well as improving the facilities to satisfy the people who visit the moon. This is just one of the possible plans, but this plan can be changed because of main factors. And I will mention about the factor that will affect to the water extraction facility building process. These are the figures that indicates different way to extract water from lunar regolith. The difference between them is that the one on the top excavate the regolith in PSR and transfer the regolith to the place where they can get sunlight and then do the rest of the process. On the other hand, the one on the bottom excavate and extract water in PSR and transfer the water to the place where they can get sunlight. Both of them have pros and cons, but it really depends on the amount and the form of the water in regolith. That is why we need to do the exploration and discover about water on the moon and make this water extraction facility plan to be more solid. And next slide, I will talk about the experiments that we have done and the exploration service concept. The plan for our exploration project is aiming to discover the location, form, and the concentration of water. The picture on the slide is the device that we have been working on for lunar exploration around 2025. We are planning to put this device on a rover and do the experiment at several places on the moon. This device consists with 3 major parts: drill, water evaporation system, and the water measurement system. The drilling part will drill a hole to gather the regolith, and the gathered regolith will be transferred to the box on the top, which has water evaporation system and the water measurement system. Water evaporation system heats up the regolith to vaporize the water, and the vaporized water will be sent to the water measurement system. The purpose of making this device is to measure the concentration of water in regolith. This is the desired system requirements in previous slide. We have been trying to develop the device which meets those requirements, and possibly we can make it lighter and smaller. And this is the experiment we have done for drilling and regolith sampling part. We are aiming to get the regolith information at certain depth of moon surface. And this experiment was for making sure that we can get soil from where we want. Now we have been working on the water evaporation system, and it will be attached to the water measurement system that is built by Yokogawa Electric Corporation. I'm gonna address the equipment in next slide. This is the water vapor measurement equipment that was built by Yokogawa Electric Corporation. This device detects the vaporized water by the laser mounted on the device, and it measures the amount of water evaporated from lunar regolith, which tells us the percentage of water in regolith. I've been talking about the big picture of our plan and the technology development, but let me mention about the service that we are planning to provide. We are planning to build a team for the envisioned service with those companies we have been working with, which are listed on the bottom left of the slide. Other than those companies, we are planning to collaborate with companies which use remote sensing satellites to the research on the moon's surface. The service will be measurement module, exploration service, and the lunar resource data. We expect our customer to be government, space agency, mining companies, and the lunar infrastructure developers. For space agency, Moon is an important base for exploration on outer planets, in addition to the purpose of scientific exploration. And in near future, we believe that the companies which are specialized in, we believe that the market in space industry will expand, which increase the number of companies which are specialized in space. We hope that we will be able to provide those information to them and contribute to the science and technology. In conclusion, it is expected that the Lunar Society will emerge and develop in 2030s, and the water resource will play the major role. To construct the society on the moon, getting the information of water is essential for the coming Lunar Society. Lastly, we are planning to provide the lunar water exploration service that will contribute to the development of the society. That's it. Thank you so much.
Thank you very much. A very interesting presentation and a nice integration of the technical aspects and the future-looking business aspects. So thank you.
Thank you.
I apologize. We're a little bit short on time. We're a little behind the schedule, and so we don't have time right now for any questions. But if you don't mind, perhaps if there are some questions or discussion later, we might do them by email.
Okay.
So thank you very much. I'd like to turn now to Maria Antonietta Pereno from Thales Alenia. Maria, I believe you are with us.
Yes, John, I had many problems before, so I hope that I will be able to share the screen. I cannot hear you right now.
I'm not speaking. That's okay.
Okay. Can you see my screen? No.
Not yet.
John, I must say hello to my friend Maria.
Ciao, ciao, my dear. Ciao, Madhu. Lovely to see you. And in fact, to know that there are many friends connected.
Absolutely.
Yes. Just tell me if you can see my screen.
We can see it now. It looks wonderful.
Very good, very good. So I'm very glad to share with you the different activities that our company, Thales Alenia Space, is carrying on regarding moon exploration. And I like to start from our, basic point, the International Space Station and the new platforms that are under development in low Earth orbit. Why that? Why we speak about the moon and I start with a few views about low Earth orbit, because what we learn in developing the International Space Station is key to prepare and assess and develop the new capabilities required for further destination, for deep space missions, in fact. Why that? Because of the lesson learned related to in-space operation of different elements, pressurized modules, payload, the way we can handle logistic operation, for example. It's important to recall what we learn on board the space station, because for sure we need to improve the future elements by using, for example, new materials, lighter structures, modular system. We'll for sure need to talk about regenerative system for life support, new technologies and tools will open up deep space to humankind. And also is important the International Space Station and any infrastructure in low Earth orbit to be regarded as in-space test bench, meaning a place where we can validate the technologies to complement what we are doing in our laboratory on this planet. And last but not the least, for sure, our experience on board the space station is vital to understand how humans can live and work in a very hostile environment.
Maria,
Yeah.
you are still on your first cover slide. Did you intend to advance the slides?
No, that is the problem I had
Okay.
with Dallas. There was always a view graph behind for me. So you are viewing what?
Just the cover slide.
No, I am progressing with the slides.
Yeah.
You cannot see them?
Not yet. Could
No.
you want to go to slideshow, because you're on still the view of your PowerPoint application. Now you're advancing.
No, for sure I am on the slideshow, but I keep it like that. So this is the title view graph, okay?
Yes.
Right?
Yes.
Okay, this is the second one, the starting point. Can you see that?
Yes.
Okay, good. Then I use this system. So I was just listing the many plus, learning plus, that the infrastructure in low Earth orbit can offer us to, further explore in deep space. And I mentioned the lesson learned, the technologies and the new elements that we can validate in low Earth orbit prior to use them in deep space. And I was underlining the importance of using the International Space Station to study physiological and psychological aspects and to understand the gap that still need to be filled with respect, for example, to radiation protection, to the need of privacy, to the need to offer the crew better living environment. And I am very proud to say that in our company, we spent the last decades, plural, in building different elements of the International Space Station. And in this view graph, you saw our contributions to the International Space Station. The node, Columbus, cupola, obviously, the logistic module, all the sinuous pressurized modules that are used to meet the logistic requirements of the space station. Not to mention also payloads that were carried with the shuttle to the space station. As shown in this view graph, half of the shuttle flights carried on board the Thales Alenia space hardware, either elements or payloads. And so, as everybody agrees, the exploration is a stepwise approach. We'll need to proceed with incremental multi-step. We need new system and technologies, and this is, how can I say, an overall architecture that was discussed and agreed among and by the major space agencies all over the world in what we all know as the Global Exploration Roadmap. And so we are flying back to the moon with Orion. Our company contribution to the Orion system is via the European service module that you see in this chart. We developed that together with Airbus, and our company contribution is the propulsion subsystem, the electrical power, the thermal control, and the consumable. Coming to the pressurized elements of the gateway, again, very proud to say that we are designing and in fact welding, guys. We are welding the pressurized modules of the gateway. So our company is providing the primary structure of HALO via the European Space Agency. We got 2 important contracts. As Thales Alenia Space in Italy, we are responsible for the international habitat, and via Thales Alenia Space in France, we are building the Esprit module. For sure, there are differences with respect to the International Space Station pressurized module, because we are designing smaller system, but hopefully more comfortable. Let me show you a picture that I like a lot. It's a rendering, yes, it's a rendering of what we expect it will be the gateway in orbit around the moon. It speaks by itself. It will indeed be an important infrastructure from where the astronauts will be able to land on the moon, but also to teleoperate robotic systems on the lunar surface. And in this chart, you see how many Italian flags, and in fact, how many times our company is mentioned. As I said, for Esprit, but also for the international habitation modules and for many other systems. So I briefly mentioned that, in fact, from a design point of view, we are evolving. We are moving from internal architecture layout that are, how can I say, very busy to more pleasant internal solutions that hopefully will be able to offer to the astronauts. And so we are, in fact, you see here, working on mass optimization. We need to reduce the mass, in particular for the primary structure. We are using new smaller docking ports based on new international docking standards. Thanks God, due to the fact we don't have debris, we can plan for using a lighter meteor protection system. I already touched the point that a keyword is reconfiguration. So for very long duration mission, we want to offer the possibility to adapt the internal layout to evolving astronaut needs. Key issue, critical key issue, is the radiation protection, for which we are building sort of water walls. So water is an important material, not only for life support, but also for radiation protection. We are implementing autonomous thermal control. So each module needs to have thermal radiators on the external surface. We are dealing with a new solution to provide and to distribute the electrical power, and also for avionics and telecommunication. This is a sketch, a rendering of the water wall I mentioned before. And I like to show here some key features on the international habitation module. You see the internal distribution. We are optimizing the private crew quarters, for sure the toilet. We have a a partition dedicated to the social life, so kitchen, the table, but in addition to the life support functions, we have also some volume dedicated to scientific experiments. I already mentioned before the docking ports, the thermal radiators, and the scientific experiments that are located both inside and outside the modules. Still from a functional allocation point of view, the current approach we are planning to develop is to, how can I say, fit in the halo module the so-called noisy systems with the intention to accommodate in the international, in the HIAB, the clean and the quiet zones. Not only orbiting system, but also surface elements. So Thales Alenia Space contribution to the lunar surface infrastructures, how can I say, is regarding different elements, starting from the lunar lander. We got the contract from the European Space Agency to design a cargo lander with a capacity to deliver 1.5 ton to the lunar surface. We are working with, for sure, it's our key products, habitat, both rigid and inflatable, greenhouses, dealing also with in situ resource utilization, in collaboration with our Thales Alenia Space colleagues in UK, and mobility system, rovers, both pressurized and unpressurized. Not to forget, for sure, the important need to provide telecommunication and navigation assets. You see there are some real hardware concerning our deployable and extendable pressurized module. Here you see the pressurized rover in a rendering and the real baby that we built in scale 1 to 2. Sorry, greenhouse. I lost the view graph. Yeah. Recently, we validate our greenhouse module in at the South Pole, and it worked beautifully. So we managed to grow the salad to satisfy, to complement, let's say, the food requirement of the crew there. And I like to close with a picture that underline how difficult is the lunar environment. So we are ready to, how can I say, fight against it and provide livable solutions. And when did we start to do that? Many years ago, 20 years ago, we were already designing in our company in collaboration with space architects lunar surface modules that in fact are still, how can I say, current concepts that are currently considered. And with that, I like to close, and I hope that you could follow the presentation, because it's difficult to speak without having a direct contact with the audience, but I'm available for any question you might like to raise. And our way of working is, yes, dealing with moon exploration, Mars exploration, low Earth orbit, keeping always in mind that we do all of that for the benefit of humankind on this planet.
Maria, thank you so much.
You're very, very welcome, my dear.
So let's see, if you would mind stop sharing.
I already did that because I know you, John.
Thank you so much.
Yeah, well,
We are catching up on the time, but we're still behind just a little bit. Let me ask if anybody had one question for Maria. We would certainly entertain it since she's invited it.
Thank you, Maria, for a beautiful architecture presentation.
thank you, Madhu. It's so evident that we were schoolmates and that we are, family.
You're on mute, Madhu.
Not supposed to say that, Maria, but thank you. Good to see you.
So with that, if we can go to
And Dallas, good to see you. Good to see you, Dallas. I see the message.
Thank you.
Thank you.
if we could go to our next and final talk before the break. Jeff Montez, are you here with us? Jeffrey Montez? And it appears he is not here. And thus we immediately come back on schedule. So we'll follow up and try to find out what happened to Jeff Montez from Blue Origin. But in the meantime, let's go ahead right now and take our break. It is 7:10 approximately. The break was scheduled to start at 7:20. So let's go ahead and take a break now. It's 7:13, and we'll reconvene at 7:13 here in California. We'll reconvene at 30 minutes after the hour, and get started again at that time. So we're going to take our break a little bit early, and we'll reconvene at 7:30 California time, so 30 minutes after the hour rather than 40 minutes after the hour. And I appreciate your flexibility. So see you all in about 17 minutes.
John, did you get my slides?
Gary, I'm on break.
Okay,
But yes, I did.
great, thanks.
good morning, or good afternoon, or very late good evening. Are people coming back online?
Here, John.
Very
Some
good.
of us haven't quite escaped, but yes.
That's all right.
Yeah. And fear not, John, I do not intend to present all 28 slides in detail, but some of the pictures there are, I think useful to have in a deck on a standalone basis.
No, understood. So the I have not yet heard back anything from Blue Origin, from Jeffrey Montez. So I'm rather assuming that he's either been overcome by events or something. Forgive me, Gary, you were going to say something else?
Oh, I was just going to ask you about your estimate of when you expected to get to my presentation.
So we're gonna talk just briefly about the use cases again that I've introduced to the workshop yesterday. It's now a little after 7:30, and I want to just check and verify whether Shinohara Sensei of Kyoto University is with us at this time.
Okay. Well, I am prepared whenever you need me. I'm not far from my desk. I'm trying to solve some structured wiring problems. So I'm listening. So I'll stand by. I'm flexible. Very
good. It's very late in the evening in the Kyoto at this point. But let me ask again, Shinohara Sensei, are you with us? Yeah, he has a much better reason to potentially have gone to sleep.
What is the time there, John?
In Japan, I believe at this point, and if Inatani Sensei is still awake, he can correct me, but I believe it's coming up on 2 o'clock.
Okay, that's very early morning. That's right.
Oh, there's someone has just come into the waiting room. And we'll give it just a few more moments. And anyone who didn't arrive today, I'll see about coordinating them and circling them up during our last day tomorrow. Gary, what are you doing?
I have part of bringing up the new lab that I built is the 6-way. I'm installing 2 6-way blade servers, and there's a cross connect between the lab, the office wiring room, and the garage.
It's okay. Too much detail, too much information. It was your screen. The background generator on Zoom did a very interesting thing. When you stood up and moved into the background, it did not fuzz you out. It kept the rest of the room fuzzy, and you continued to be crisp.
Huh.
So that's very interesting. That suggests that it's based on recognizing you as a person as opposed to distance.
Indeed. Well,
So
it's,
it was very interesting, actually, very interesting visual effect of you, crisp and clear, standing and doing something on something that was very fuzzy and less than clear.
and that's an awful lot of what I do, John.
So true, so true. Okay, so we are in fact more than halfway done with today's discussion. So I don't want to delay us any further. Although if we get too far out in front, of course, this is a multi-continent and a multi-hemisphere event. Stephen Durst from Hawaii is several hours behind California. And so he may not be anticipating joining us quite so early, but we'll see how that goes. Gary, you may be coming on earlier than I expected.
As I said, I wanted to make myself available whenever it needs to.
Very good. Thank you.
I certainly have plenty to talk about.
Oh yeah, I understand that. I understand that. Okay. So I wanted to just review the bidding for a moment with regard to these use cases, which I'm using as a strategy for elaborating on the prospective uses of the building blocks within the OASIS 25 reference architecture and the kinds of systems and resulting specific cost limits that might come into play. In this morning's conversation, so yesterday I mentioned that there are two use cases for propellant services in lunar orbit. One involving propellants sourced from the moon, and one involving propellants sourced from Earth. We had another useful input this morning from Chiyoda Corporation, which highlighted that in fact there are
train operators looking at a single wet bead, and we don't have a lot of like pictures of that. So I would be really resistant to offer up anything
somebody
concrete
has got their mic open.
Like,
Is that you, Gary? Melody, that must have been you. Okay, thank you for muting your mic. As I was saying, this morning we had a useful reminder that and I should say, of course, this meeting is being recorded. We had a useful reminder during the presentation from Chiyoda Corporation that there are two primary options for fuel production from lunar ices on the lunar surface. One being the mining of the ice-bearing cold lunar regolith, and then its processing in a different location where solar energy is readily available, and the other being the processing of the ice-bearing lunar regolith in situ in the permanently shadowed region. And so this might be a useful case 1A and case 1B, as it were, in going forward. We also saw in Atani Sensei's presentation on the Moon Village evolution team results, and also from Dallas Bienhoff's discussion of the sort of the assessment of the Starship as a killer app, as it were, for lunar transportation. Some discussion of significantly higher numbers of lunar visitors than are contemplated at this time for the 2045 timeframe, which is relevant for the OASIS 2045. And so that I also pose a very useful sort of out there variable for the future of the case studies. I'm looking forward to our discussions this morning. We'll see if Shinohara Sensei from Kyoto University is able to join us, but if not, then we'll certainly understand. We're now at 7:40, and in the interest of, oh wait, Shinohara Sensei, you have joined us.
Yes, I'm here.
Very good. A good morning or very, very late evening.
Oh, no, good evening, good night. Japan is in the midnight.
I'm so sorry.
No.
So it's very good to see you. If you are ready to proceed, please go ahead and go forward with your presentation.
Oh, it's time to start. Okay.
It's time to start.
So can you see my screen?
Yes, we can.
Okay, so thank you so much. So thank you for inviting me to this great workshop. So I'm so sorry I'm late to attend it. So because Japan is in midnight now. So last year, 2 years ago, I attended this workshop, Moon Village workshop. And at that time, I introduced one possibility of the moon experiment of the wireless power transfer technology. So today, instead of the moon experiment itself, I'd like to introduce a roadmap to the moon, to the solar power satellite via moon of the far-field wireless power transfer technology from business. Because before we go to the moon, we must expand the technology from the business side. So fortunately, recently, business of the far-field wireless power transfer is expanded, and there are a lot of startup companies in US, in China, and in Japan. So today, I would like to introduce a business side technology of the far-field wireless power transfer to the solar power satellite via moon. Yes, so as you know, all this is a conceptual image of the solar power satellite. So this is a very huge space solar power station. So some people consider it is not possible because it's very huge satellite. But only a problem is just the size and the weight of the satellite itself. So I think we can build the solar power satellite in near future. And key technology is wireless power transfer technology, as you know. So now this is a Japanese roadmap to the solar power satellite by Ministry of Economy, Trade and Industries. Now we are in 2022. So we had already 2 steps, and additionally now we are in third steps. So we have already done the 2 R&D of the wireless power transfer technology until the 2018, and now we are in the third step to carry out long distance wireless power transfer and to develop the sandwich structure with solar cell and wireless power transfer systems. So as a next step, we Japanese consider the satellite experiment, and fortunately, the first step of the satellite experiment in Japan has advanced a little. So at the end, in the end of last year, just so three weeks ago, Japanese government decided to carry out the small satellite experiment of the wireless power transfer towards the solar power satellite. We will get the budget from the Japanese government. And but today I don't have enough time, so I'd like to introduce spin-off or spin-in technology for the wireless power transfer business to the solar power satellite. And this is my perspective of the wireless power transfer in next decades. So now we are in 2022, and it's a decade of the commercialization of the wide beam wireless power transfer via microwaves. So wide beam means we provide the wireless power to multi-users with low powers. So this is like a smartphone, and this is like a Wi-Fi technology, and but this is a very convenient technology for users. So a lot of company, a lot of startup company, and a lot of government are interested in this wide beam WPT technology now. So briefly, I would like to introduce the current status of the commercialization of the wide beam WPT in Japan and in the world. So this is a market perspective of the industrial far field WPT in 2025 in Japan. So for factory automation, IoT sensor network, or sensors for nursing house watching, or to a wireless charger, we Japanese are expecting such a big future market with about $5 billion. So based on this market perspective, now a lot of Japanese companies started to develop the commercial WPT system, and the Japanese government decided to establish the new radio regulation for the wireless power transfer. 10 years ago, we could not consider such a good decision by the government. So this is introduction of the commercial WPT products in Japan. Sorry, it's in Japanese, but I'd like to explain simultaneously. So I established a consortium with a lot of companies, and the Japanese companies, and this is one example of the WPT commercial system by Panasonic Corporation. They named this wide beam WPT commercial system NS-Figures, and they are considering about the WPT for the nursing house application. So it's a wide beam WPT system, and the receiver can receive a very low power, but it's enough to drive the sensors. And this is not a Japanese technology, but this is a US technology, OCIA startup company. And Japanese company collaborates with OCIA, and they are promoting their wireless charger system to Japan. And this is a Japanese startup company, Space Power Technology Corporation, and now they are transmitting the wireless power to drive the actuators and motors. This is the first Japanese startup company, and this is a battery company, and I should skip it. And I would like to introduce last one. So this is a future technology of the wireless power transfer to check the infrastructure with battery-free sensors. So by driving car, we are transmitting the wireless power transfer. This is a movie of the real field experiment in last year. So I skip this. And this is a technology from US. Now, the startup company, PowerCast Corporation, is producing this wireless charger for the Nintendo Switch game machine. So this is a very interesting wide beam WPT commercial system. And the amazing point is this: you can buy it on the Amazon.com now. In US only because it depends on the radio regulation in each country. But this is, I think this is a first commercial product for the common people's B2C systems in US. So 10 years ago, I couldn't image this future. So, and for the commercialization, we need new radio regulations because there is no special frequency for the wireless power transfer. And from 30 years, 40 years ago, US NASA was Japanese JAXA. Okay, so now we started the discussion to establish new regulation for solar power satellite and wireless power transfer 30 years ago. But recently, mainly for the commercial system, we keep discussion with victims, the conventional wireless application guides, and in each country, we are making the new radio regulation for the wireless power transfer. But in each country, unfortunately, there are some way how to consider, how to treat the wireless power transfer frequency. So, for example, in Japan, Japanese government considers WPT as one of the radio application with license. So it's very strict regulation in Japan, unfortunately, but this is the first formal regulation of the wireless power transfer in the world. And in US and in China, they consider the WPT as one of the ISM application. ISM means industrial, scientific, medical application. So it's the easiest way to publish the commercial WPT system. But there are some problems to consider the WPT as an ISM application, but so they keep discussion now. And in EU, they have the other way to consider the WPT as one of the short-range devices. So now we work together, but in the different world now. But so it's very good chance to establish a new radio regulation in the world. So as I told you again, so 30 years ago, we started the discussion for the WPT for solar power satellite. But there was no hot discussion and we didn't get a new radio regulation during these 30 years. But recently, for the WPT business, we can get the new regulation for the wireless power transfer. It's very good chance. So, for example, now we Kyoto University studied the collaborative research with the SoftBank. SoftBank is one of the biggest smartphone company in Japan, and we collaborate to promote the simultaneous communication and the WPT system. Japanese government is supporting this collaborative research with Kyoto University and SoftBank. So we started it from the 2 months ago. So this is a very good around the project from now. So please expect our future results. And in this decade, of course, we must advance the satellite experiment of the wireless power transfer. So in Japan, we have already started small satellite experiment named Delight. And the aim of this satellite experiment is to expand the large structure itself. So as you know, solar satellite is a very large and huge structure of the solar cell and antennas. So JAXA focus on the structure, a large structure expansion, mainly in this Delight experiment. And they will carry out this experiment in next year. And so we get the other project budget from Japanese government. And this is our this is an example of our proposal for the satellite experiment for 2025. This is a different experiment. Now in Japan, we have two satellite experiment projects. One is Delight, and this is just proposing experiment. So we must start to design this next satellite experiment, and in this satellite experiment, our aim is to transmit wireless power to the Earth. So this is an ongoing satellite project in Japan in this decade. And next decade, from 2030, I expect to promote the commercialization of the narrow beam, focused beam WPT, like the solar power satellite and like the moon systems. So we have already studied the commercialization of the narrow beam WPT. This is one example from China. Maybe you know, Xiaomi studied the millimeter wave WPT wireless charger for smartphone. Xiaomi is one of the biggest smartphone companies in the world, like the Apple's.
将能量通过毫米波极窄波束的形式传递给手机，在半径数米的空间内实现了5瓦的远距离无线充电黑科技。不仅于此，还可多设备同时充。
And in New Zealand, I found this very interesting startup company, Emerald. So their aim of this their aim is a long-range wireless power transmission. So of course now there is no radio regulation, and there is no market of the long-range narrow beam WPT even in the New Zealand. But they gather some fund budget to develop the long-range wireless power transfer as a startup company. And now I became one of the technical advisors. So I expect the future of this Emerald Corporation, New Zealand startup company. So of course, in this decade after 2030 or 2040, we expect to carry out the WPT experiment on the moon, and we will build the moon village in the next decade with wireless power transfer technology. So this is one cartoon proposal of the WPT on the moon or to the moon. From the moon orbit, we can transmit the wireless power, and from the moon base, from the moon village, we can transmit the narrow beam wireless energy to drive the rovers on the moon, for example. This is next decade's expectation. So that's end of my talk. After 2050, we would like to build the solar power satellite, BR Moon experiment, and the BR Moon village. So this is our future image of the Earth and space technology. So this is our image named Sustainable Humanosphere with wireless power transfer and solar power satellite, BR Moon. So thank you so much. That's all my talk. Thank you.
Dear Shinohara, thank you so
Hi.
much. That was a whirlwind, lots of information, very interesting,
Mhm.
and I think a very really a lot of food for thought because of the commercial pathway to future development. I will say only one thing about your last couple of slides, and this is just a comment. So I think that the acceleration of the first Japanese low Earth orbit space to ground demo, because frankly, from the standpoint of the last few years and the slow schedules and so on, that this is really shocking. And it will be like an electrical shock on all of the planning for SPS, I believe, SPS and WPT. And so when you say SPS in 2050, I think there is a pretty good chance, not 2050, but maybe 2040 or 2035, that this time will collapse because now Japan is moving forward and everybody must catch up.
Thank you so much. But as you know, of course, now US started a very excellent project named Spider.
Yep.
And as you know, China also started their big project towards a solar power satellite, and they have a very huge budget. So in US, in China, and in Japan, we need a cooperation to realize the Moon Village and the solar power satellite. I really think so.
Yeah. No, I think everyone on this call certainly agrees with your perspective. So any questions or comment or discussion with Shinohara Sensei before he can go to bed?
John, if I may, I thoroughly enjoyed this presentation, and I particularly liked the idea that this can be a consumer item before it can be SPS, John. And that is a reverse view of how beaming energy can come to Earth from Earth. The question to the good professor is, we have a consumer electronics show in Vegas. Did you present this there?
Not yet. So you mean CES? So,
Yes.
but some US startup companies has already shown their commercial WPT technology, and they got some CES hours. So in each year. So of course, I'd like to introduce a Japanese technology in CES. So I expect after COVID-19 pandemic, so I'd like to visit Vegas and CES with our WPT technology. Thank you so much.
Good luck with it. Thank you.
If you come to Las Vegas, Shinohara-san, please also come to California. You can visit with Madhu and come for a barbecue at my ranch.
Yeah, thank you so much. So maybe Mr. Gray.
Sonora Sensei, this is Gary Barnhart. One of the things that seemed also striking to me was the idea that you're moving towards the notion that the customer requirement is what is being met, and the technology that's used to accommodate it is in large measure transparent to them. Being able to essentially treat it as a frequency agnostic problem, whether or not we're using millimeter waves, microwaves, or infrared or optics. It's whatever it takes to meet the customer requirements. Seems to be a useful opportunity for convergence, both in terms of how we actually serve the customers, and how we deal with the back end electronics and what it takes to be a utility. So there, it seems that there's a tremendous opportunity for cooperation and collaboration, where we effectively grow an ecosystem of cooperating and collaborating companies in governments to realize this. And you know, to the extent that we're successful, I think your timeline may end up coming in closer.
Thank you so much.
Which would be very, very interesting.
Yeah, thank you so much. So now, for example, US and the Japanese government are interested in the wireless power transfer. And of course, US government, FCC, Federal Communication Commission, now they allow the startup, US startup companies to use some frequencies for the commercial WPT system already. And of course, in Japan, within 2 months, we will make the new radio regulation for the commercial application, and some startup companies are born. And of course, it's a very good chance, and but we need a collaboration. So I really expect to harmonize the governmental issue and the company and R&D from the, for example, university and the organizations in future. I think so.
Yeah, being able to reduce the systems engineering to practice would be, I think, extraordinarily useful. Much like if you have in a conventional electrical load problem on Earth, you have a load that has some power specification that is some distance from a generator, and you can literally take those data points and go to a wiring table and say, this is what I have to do.
Yeah, thank you so much.
To support that. We need to be able to do that with respect to wireless power
thank
transfer.
you so much. For example, 10 years ago, we developed a very excellent technology of the phased array, but it's very expensive technology. But recently, some startup company is developing the very cheap phased array for commercial applications. So this is a very good advance. We didn't consider this cheap phased array not only for solar power satellite, but also for the commercial system. But recently, now they are developing the very cheap and useful phased arrays. And of course, we can apply this good commercial technology for space on the moon. I think so.
Yeah, and just to interrupt, we do need to move on in just a moment. But okay. I think one of the most significant and powerful aspects of this kind of development, the one you were mentioning a moment ago, Shinohara-san, is that once someone does it, it proves to everybody else that it can be done. Yeah. So SpaceX does a low-cost reusable booster, and now everybody is developing low-cost launch. Yes. So if you only have expensive phased arrays, obviously they must be expensive. And suddenly one company does a cheap one, and now everybody knows it can be cheap. So I think this is going to be true over and over and over again with regard to the development of the moon. That everybody knows it's billions of dollars, and then suddenly, well, no, it's not so bad. It's maybe 100 million, or maybe 10 million, or maybe 1 million. So it's once you have the revolution, it's hard to go back. Gary, you still have your hand up. Let me just say, Shinohara Sensei, thank you so much for your stimulating presentation. And it's a very useful update on the situation internationally in Japan and commercially. So we have not heard anything from Blue Origin or from Jeffrey Montez, so I'm assuming he is not available or some other problem. So we will go ahead with today's program. Our next speaker is Gary Barnhart. Take care.
And hope the professor gets some sleep.
Yeah, get some sleep, Shinohara Sensei.
Yeah, sorry, I go to bed.
No problem, no problem. See you in Las Vegas.
See you. Thank you so much.
Okay, so please, Gary, you have the floor.
Okay, I'm just adjusting the shared screen approach here. And okay. Okay, you should start. Does that fill your screen up reasonably well?
That's just perfect. And
Fantastic.
Gary, if you could speak for about 20 minutes.
That will be that'll be the plan. I'll put us on the great. Okay. My talk is going to be on space solar power and ancillary services beaming, realizing the promise of the Lunar Power and Light Company. I'm Gary Barnhart. I'm the president and CEO of the Extraordinary Innovative Space Partnerships, Inc., XISP, Inc. for short. And we're a Moon Village Association member. From a background standpoint, I have been involved in pretty much every side of the table in the space business. Both government, large commercial, small commercial, and nonprofit. Since the early '80s, and I'm a robotic space systems engineer that has gotten heavily involved in both power and ancillary services utilities. When we think about the challenges of power beaming and ancillary services, there are multiple venues that we have to end up addressing: space to space, surface to surface, space to alternate surfaces such as the moon and asteroids, and space to Earth. Each of those venues involve flows of information, services, energy, resources in general, and there is an evolution from technology development work on the ground to space, to demonstration work, to deployment of systems as work vectors. This is actually a very detailed, high-resolution image that I encourage you to look at electronically at your leisure. But the intention is to try and provide a visualization of the arcs of opportunity that we're faced with. Another view of this is something called we call the Space Solar Power Challenge Matrix, which we were asked to put together for the Air Force Research Lab. And this puts words to this idea of the evolution of TRL advancement that I was alluding to, as well as the different venues that are involved, and a number of things that one can look at in terms of the relative value of delivered power. And the idea is that for any mission objective that you identify, you should be able to go through the challenge matrix and see what it is that you can do to help further the achievement of that objective. In terms of the mission objectives overview, there's a number of elements that we see. One, the unbundling or disaggregation and reoptimization of space electrical power systems. It becomes more about how you serve the customer than the elegance of a particular one-off solution. We want to be providing beamed power and ancillary services as a utility. We want to support the further development of beaming technology, because I believe in large measure it's at its infancy. We want to reduce the systems engineering involved to practice. We see the need to divide the work into 3 linked phases that are both iterative and recursive in terms of technology development, demonstration, and deployment, really trying to bridge the technology development valley of death and converge what we consider to be the frequency agnostic solution space. From a technology, I think that that's where we need to be. From the particularities of serving customers, we have to deliver whatever it takes in terms of technology to actually service those customers. This notion of a TD-cube mission defines a civilian non-weapons use of space solar power. It addresses both real and perceived cost, schedule, and technical risk associated with space solar power and ancillary services beaming across the multiple venues. And it fosters an implementation of beamed energy systems as part of an interoperable end-to-end power generation, storage, and distribution systems. So far as the market development, what we're aiming for is to provide commercial power and ancillary services to support lunar operations. SSPB as a utility service to customers, not as a client-facing research project. In large measure, you could think of it as, I think we need the equivalent of Bell Labs support that they, provided, the development of telco companies, that have that be, an internal effort, and the utility service we provide customers is we give them power, we give them the ancillary services, and it just works. Ancillary services include command, control, telemetry, and payload data, relay, as well as time and navigation support. When you talk about doing, space solar power, beaming, you're also talking about ancillary services because you have to have the control links. With respect to what we're delivering from a power standpoint, initially, it's a power augment for certain operations, then to keep alive power, then operating through the night, then general operations, 24/7 operations. It needs to be incrementable, scalable, and interoperable modular building blocks. And we need to grow to support enhanced power requirements for exploration, proving reserves, ISRU demonstrations, infrastructure operations, and even augmented propulsion for transportation, both to and from the surface of the moon. And there's multiple opportunities for what we envision as loosely coupled, modular, and multiplexed architecture. You got to start someplace, though, and we generated proposals for a space-to-space test bed. In this particular case, it shows a notional space station mounted transceiver and a 6U CubeSat test article in those regards. I don't know whether or not this shows through through the link, but one of the things that we were what we were trying to address with the test bed is the need to characterize, optimize, and operationalize the technology. Another key aspect of that is that you have to be able to communicate to different potential customers and supporters and investors what it is you're actually doing in a way that they understand. We came up with the idea that you actually build in a visualization capability into the test arrays so that you can see to the extent that you're succeeding with respect to the transmissions. and how things are aligning themselves, which is an interesting thing that happened to be shown in the slide. In terms of the building blocks, and, in ways to foster technology enhancement, an approach of rapid prototyping and proto-flight, which allows for incremental investment and returns, we think is absolutely critical. Basically, for every increment of resources you put into one of these projects, you need to be serving one or more actual customers. That's the essence, behind the methodology of the TDQ mission design. We need to be able to provide for the near real-time quality of service characterization of both power and data links. I think there's opportunities with respect to the evolution of reflect array technology, merging both rectennas, for power receptions, transmit and receive antenna and photovoltaic arrays. Being able to provide visual and other means of affirmation of link delivery and service. There's opportunities with respect to the evolution of cognitive software-defined radio to support sensing available links and the different control aspects. Evolving to the dynamic scheduling of power and ancillary servicing links, as opposed to a highly manual, scheduled, bed pipe approach. We need to foster facilities architectures rather than unique non-interoperable solutions. When we started on the quest for the external utility ports for space station, we were told we were on a fool's errand. NASA doesn't do business that way. If you need electrical power, NASA designs a power supply and in the end-to-end system. The concept of an electrical outlet, that would be a radical thing. Well, that's where we went. And that's it. That's a critical to this view of a facilities architecture. We have to provide for secure authorization, authentication, and control of power beaming. This can support an evolution towards autonomous navigation and situational awareness through the relay nodes, and as well as support pervasively networked interoperable network communication architectures. A way of envisioning this is a power and ancillary services utility supporting an ad hoc mesh network of customers. With respect to critical considerations, we see space power and ancillary services infrastructure as both an applied engineering problem and an economics problem. Key to the fact that it's an applied engineering because the solutions are valued in terms of availability, durability, resilience, and maintainability, not as new science or engineering. In economics, because the solutions are necessarily sustainable utilities that will circumscribe what's possible. So we think these challenges are best realized by leveraging a combination of technology development push and mission requirements pull, driven by the different fundamental figures of merit and value proposition for each application. I alluded to the work vectors earlier in terms of development, demonstration, and deployment, and the different venues involved. We think each increment of public and private investment needs to lead to an operational capability useful for one or more other missions. And the efficacy of any systems architecture must consider the entire life cycle of the fielded equipment. And the engineering solutions which leverage other mission investments should be given priority, but not exclusivity. And we've got to grow the community of interest. We're getting a lot closer to reducing the systems engineering to practice. We have a very good understanding of the key variables that are involved, and we need to be able to exercise our and increase the efficacy in which we get this data and we orchestrate that into viable systems. This is, what I was euphemistically referring to in the past as the money chart. Why do we talk about power beaming? And it was just looking at 3 different cases. One in the world of test beds where you're dealing with very low power densities that no one would be particularly afraid of or concerned about at all, to cases where you can more than double the datum that which we used, which was the solar constant, where you can start thinking about actually serving customers. And then the third case that we looked at was where you could deal with power densities that were an order of magnitude more than the solar constant, at which point you can really talk about being, functioning as utility to multiple customers in those regards. This is just some more details. It turns out for stuff on the space station, being able to press towards robotic compatibility for all of your interfaces, and to be able to both locate and move the equipment around ends up being very useful. And we're talking a comparatively reasonable scale. This is this entire system is less than the standard form factor used for the GEM exposed facility. And it could be compatible, with the Columbus exposed facility, Bartolomeo, the GEM exposed facility, and also, we've evolved the design to be able to be accommodated on different pressurized logistics carriers, and hopefully in commercial modules to come. From an applications and customer perspective, what we're providing is intended to support an expansion of operational mission capabilities, power densities, as I said earlier, an order of magnitude above the solar constant, multiplex power and ancillary services, enhance spacecraft and infrastructure design flexibility, and there's some angles with respect to outbound orbital trajectory insertion propulsion, and pave the way for the Lunar Power and Light Company. Applications from a government perspective could also include sustainable and interoperable high power generation, storage, and distribution. This evolution of frequency agnostic extension of the cognitive software defined radios, and in a very real sense, operational flexibility plus situational awareness equals enhanced space power, all on multiple entendre intended there. Let's see here, why is it not going down? Okay. There we go. Sorry. So I indicated, there's an opportunity with respect to, the pressurized logistics carriers being, repurposed for formation flying operations, in supporting other crew-tended space manufacturing elements that may evolve, and this notion of a cislunar utility needs to look at the different markets that would be served in those regards, and what are the figures of merits for those markets. From a technology challenge standpoint, the physics of near field and far field energy propagation seem to be fairly reasonably understood. However, the use of radiant energy to transfer power, data, force, and or heat, either directly and or indirectly by inducing near field effects at a distance, are not well understood. Moreover, there's a very limited engineering knowledge base of practical applications. Accordingly, this is applied engineering work, aka technology development, not new physics. And to optimize beaming applications, we need to better understand how each of the components of radiant energy can be made to interact in a controlled manner. Basically, we need to build and fly the test beds to make this real. Boom, come on thing. Okay, boom. So the the radiant energy components include electromagnetic, linear and angular momentum, thermal and data, and their potential direct and indirect uses for each of the beam components. And any combination of these components has implications for all of the spacecraft and structural systems that are involved. In theory, the use of the component interactions can enable individual knowledge of position and orientation, shared knowledge and loose coupling of interfaces between related objects, near network control, size descents, proportionality to enable desired control, potential for fixed and or rotating planar beam projections. We saw that in the Internet of Things stuff presented earlier, and the potential for net velocity along any specified vector. And we should have to bear in mind, in theory, there is no difference between theory and practice, but in practice there is. In terms of additional challenges, from an economic standpoint, we have to map the financing to terrestrial electrical power and ancillary services utility analogs that just so happen to be in space. In each addressable market, we have to identify and codify the different fundamental figures of merit. From a public and private partnership standpoint, we have to draw out the confluence of interests that can support substantive agreements. And from a geopolitical standpoint, we have to make international cooperation and collaboration real. We have to put these on unrealistic timelines. This is very much, as we've heard from earlier folks, the timelines for the evolution of space solar power are in a state of flux. The key thing why I'm still including this chart in this deck is this idea that for these sorts of TDQ missions, we need a series of both iterative and recursive milestones. It's an ongoing process. It's not a just one thing, one and done. We have some examples that can be gone through with respect to what you can do right now with the technology that we have. And the issue comes in is how we can start doing something real and create a test bed environment where we can evolve it as part of the process of actually servicing customers, not just as an interesting laboratory exercise. And this leads to the evolution of how it is that we can be an integral part of serving a lunar village, if you will. We think that power and ancillary services beaming is going to be an integral part, necessarily an integral part in any interoperable, scalable, power generation, storage, and distribution system on the moon and throughout the different venues in space. From a next step standpoint, our space-to-space power and ancillary services beaming commercial TDQ mission is moving forward with the advice and consent of the cognizant NASA mission directorates. We have requested that NASA fully activate the negotiated and approved Space Act umbrella agreement that we have on implementing implementing TDQ missions. NASA direct and indirect funding is not precluded through other agreements and solicitations, but won't be allowed to be a barrier to moving forward with the mission development and execution. In parallel, to ensure that there's a assured path to execution, direct commercial purchases of service agreements are being worked consistent with the enacted NASA commercialization policies. We're actively seeking additional partners, participants, and customers across commercial, academic, nonprofit, and government sectors. And there's real opportunities for international cooperation, leveraging both the ISS agreements and the Artemis Accords that are being developed. And the balance of our funding, cash and in kind, will be raised from the SSPB consortium investments that we're pulling together in a combination of XISP and debt and equity financing. In conclusion, as we see it, space solar power and ancillary services beaming has transitioned from a conceptual mission pregnant with opportunity to a commercial mission with recognized standing. There's now a defined confluence of interests biased towards successful execution of the mission as a public-private partnership, and the successful demonstration of space solar power beaming will reduce the perceived cost, schedule, and technical risk of space solar power technology and pave the way for its use in multiple venues. Bottom line is, don't wait for the future, help us build it. And what's next? What we see is the Lunar Power and Light Company. Thank you very much for the opportunity to present this. There's a few other resources that are in the slide deck, which will be made available for all concerned. Thank you for, as I said, thank you for the opportunity.
Thank you,
And
Gary.
That's it.
That's very good. And we have, I noticed, if you would mind stop sharing.
I'm working on that right now. Susie, get it to make it available. Where is?
We're looking at your desktop.
Yeah, I understand. I just have to get the screen to come back. And
I was in a workshop a few months ago where a gentleman, I think it was in Korea, he was in Korea. He was screen sharing and he left the meeting without stopping screen sharing. And then we were stuck with his screen for the rest of the meeting, unless something. So it was challenging. We still got you.
yeah, I know the controls have disappeared for some reason. Well, I can entertain any questions while I find the controls, and we will.
There
we go.
No, I did it.
Great, thank you.
I cut you off from here.
Great.
Okay, very good. So we need to move on because of the time. I apologize, but I'm sure Gary would entertain any further comments and presentation or discussion going forward. It's my pleasure now to introduce Stephen Durst, who is with us. I believe Stephen is based in Hawaii still.
Hi, aloha, John from Palo Alto, California.
Oh, well, you're in Palo Alto,
north,
so it's not so bad.
Yeah, I'm working out of our original, still operating California office before traveling out to Kansas tomorrow for.
Wonderful.
interest.
So, thank you so much for joining us. This is we did not last year at the 2020 MVA architecture workshop. We did not have a presentation on lunar surface science, and so I'm hoping that your presentation today will open a whole new front of discussion and information to inform what we're looking at with regard to future systems, operations, and opportunities vis-a-vis the moon. So please, Stephen, let me turn it over to you. You have permission to share screen.
Well, thank you, John, and you can hear okay?
I can hear you just fine. I will just remind you, because I know you came on a few minutes ago, that we are recording this session.
Understood. Thank you very much, and thank you, John and Madhu and Giuseppe and the whole Moon Village Association for moving forward and making this workshop possible, including ILOA. Appreciate that. Big supporter. So I will try and as I told John, working out of our original Space Age Publishing Company ILOA office here in Palo Alto, which we've maintained since 1977. I will now try.
It's a pleasure to see you, and we are looking forward to your presentation.
Well, I'll see what I can do. Thank you, Madhu. Good to hear from you too. So share screen. And if I do that, and that, and let's see, go there. And there we are, I hope.
Not quite
And
yet.
that's visible okay there, John?
That's good.
okay?
You might want to go to full screen. We've got the sound of a
Full screen,
modem. We've got the sound of a modem in the background. Perhaps someone, I don't know if that's you, Stephen, or someone else needs to mute.
I don't believe
Nope, it's gone now.
Here, I hope
it's
okay.
gone now.
Okay, and it looks like from here that it's a full screen.
It is
And
now. It is now. It looks great. Please go right ahead.
And there's what we're talking about, 20 minutes, John? About
20
that?
minutes, please.
Sure. Let me just set my timer here. Okay. Well, this is a presentation update on our organization that is based in Hawaii, ILOA, Hawaii International Lunar Observatory Association. And we will update our progress. We do have evolved over the years 5 missions that we're working on simultaneously. They all sort of flow together. Introductorily, ILOA has a purpose, long-standing, to expanding human understanding of the cosmos through observation from our moon. Fairly standard astronomical observation statement of purpose, only this time from the moon. We incorporated as a nonprofit on Hawaii Island, the Big Island in Kamoela, Waimea in 2007. Some of the very brief salient characteristics of the mission, the organization, as the ILOA is multifunction. All of us hoping to work between Earth and Moon with works in cislunar fashion. We'll be working interglobal. And I do want to say that we've been approaching our first mission to launch to the moon. It's still set for as early as this quarter, 2022. We'll get to the realities of the timing, but we've been motivated by that approach of really realizing this dream of operating on the moon. Multifunction, observation, communication, and lunar-based build-out. And as John mentioned, the science is driving us, the astronomical science, the pull of the stars, learning, exploring about the stars. Our galaxy image is a long-established first image that we'll take with our instruments and hope to catalyze astronomy from the moon, a first flight industry, which has several dimensions to it, the idea of a first flight industry. Our organization consists of a very distinguished board of directors, 27 at this point, a little bit static the last year or two, but we're going forward with new configurations now. You'll recognize some people, and I think some of you are on the call, Masuzu. So moving forward, this slide here, talking about our 5 moon missions, and I'll briefly comment on them individually, and then more in depth each one going forward. Our flagship mission, which hasn't wavered, the destination or desired destination of Malapert Mountain, the ILO-1, and we are very much looking for a ride like we've been for many years. If anybody has any ideas of how to get a small telescope or two to Malapert Mountain, the communications capability, please let us know. We're following some active leads right now. but neither NASA has opted for Malapert, nor has the CNSA in China. Perhaps Russia might be interested in there are other considerations. What we do have more immediate and more feasible is our ILO2, the original backup for ILO1, which was to go to Shackleton Rim, but not so early. We are still in considerations for a contract with Intuitive Machines and others to take us there as early as December of this year. That's what their NASA Eclipse Award was projected for, December. Nobody thinks it's going to hold because their first mission, of which we are contracted aboard, is still focusing on fixing a launch date right this moment. And I will talk more detail about our precursor mission, which, as you see, is still officially set for 2022 Q1 now, this quarter. Unofficially, we are not expecting it before June of this year. And personally, we prefer actually July. I'll mention that later. Our fourth mission, that's part of it's been completed. We have a long-standing collaboration, about 20 years now, with astronomers at the NAOC, the National Astronomical Observatory in China. We cooperated on the Chang'e 3 mission, which is now dormant on the moon, Chang'e 3, to allow uninterrupted communications and science with the Chang'e 4 that we had less, but still some collaboration with. And finally, like many of us, we're focused on a human return, and we've long advocated that for 30 to 40 years, and in particular, the last half dozen or years, the first woman on the moon. And it's really satisfying to seeing that moving towards reality. So those are our 5 missions that we are working on simultaneously, more or less every day. The completed mission that I got a little banner in the way here. I don't know how that, hold on a second, please. There we go. The galaxy imaging that was completed in late 2014, we have this collaboration, as I mentioned, with an MOU with NAOC. You can see on the image there on the right, the MOU at our headquarters in Hawaii with the Chinese official and the director of our neighboring Canada, France, Hawaii telescope facility, Christian Goye, just to my left. That's the LUT image, the first robotic telescope ever on the moon. It rode to the moon 41 degrees north aboard the Chang'e 3 lander in late 2013. And a year later, working with an astronomy team in Hawaii, we did collaborate with the Chinese astronomers to obtain the first image of a galaxy spiral ever from the moon. And you can see that image on the left, the control image that's M101, the big spiral galaxy that was imaged with the LUT and our Hawaii Lunar Astronomy Group. And that's a control image, M101 on the right. There's some detail. The University of Hawaii at Hilo Astronomy Department was key in that, as well as Canada, France, Hawaii telescope. And now Chang'e 4 is conducting very low frequency observations on the far side of the moon in cooperation, much cooperation with the Netherlands Astronomy Working Group. ILOX, we were counting down to a March launch. As I say, there's testing going on. And we are hoping for a June or July launch to conduct our first light image. That's the picture of the Milky Way there. And we have 2 small instruments going to remove this two small instruments, a narrow field of view and a wide field of view mounted orthogonally on the top of the Nova C lander. The instruments were built by our long-term partner in Canada, Canadensis Corporation. You can see some of the specs of the instruments on the right there, the field of view with the wide and the narrow rectangular. Its mass is 0.6 kilos, 5 by 5 by 5 centimeter housing, and 2 watts for imaging with a maximum 14-day. It'll be 1 lunar day's operation. Besides this galaxy image that we hope to obtain, the first image of the Milky Way ever from the moon, which has all kinds of stories to tell about it, perhaps parallel to the first image of Earth ever from the moon in the 20th century, looking back at our home planet with the tremendous impact that had and influence. Now when we return in the 21st century and look out towards our future, not just back at home, but out towards our future to the stars, to the galaxy stars. We've invited, after our first light image, which would be great, we'd be very, very happy, mission success if we get that first image. And we have a worldwide galaxy network of scientists and educators and outreach specialists to tell the story about why looking at the galaxy from the moon is significant. We've invited professional astronomers and observatory operators from around the world already enthusiastically accepted invitations to make these precursor. It's a very small instrument. They're fixed, so we have to take what the spin of the moon gives us as the sky passes overhead, but very enthusiastic preparations. We're waiting for the launch, but from observatories and astronomers around the world. And while we're waiting, we realize that we may be able to advance a long-standing objective of our mission, namely our affiliated Space Age Publishing Company, as a business plan of doing broadcasting from the moon, broadcasting our space calendar that Moon Village Association puts up on its website every week with much appreciation and support. We want to broadcast that from the moon, and we are sending up some test files to do preliminary space calendar lunar broadcasting with this ILOX mission whenever it goes later this year. So we're very excited about that. And of course, every time that it gets delayed, it's a little bit, with Charlie Brown on the football, but you pick yourself up and reconfigure and move forward. The mission objectives of our, that's the ILX, the IL-1 and backup have objectives of, again, galaxy first light imaging and astronomy. We would be tilting our camera down after that on the more advanced missions, which will have pan tilt capabilities for Earth observation. I know we talked a lot with Moon Village Association with Giuseppe Ribaldi about the increasing value of Earth observation for many, many reasons. I'm very involved in the International Astronomical Union, and one of their leading divisions is called Rotation of the Earth, a very appealing concept, rotation of the Earth as observed from the moon. And then finally, after the galaxy stars, Earth observation, we continue tilting the camera down to the lunar surface observation for characterizing the local surroundings and participating in lunar base build out. Many other applications from the moon. It's a whole new world. You can look at the entire universe and all the fascinating objects and phenomena to observe. South Pole location, I think we're all familiar with Malapert Mountain, the 5,000 meter peak, the plateau that provides line of sight observations, communications with Earth almost 24/7. High degree of sunlight, power, the weather's good. Proximity to the water ice in the permanently shattered crater, Aitken Basin nearby, for southern skies are astronomically rich. south pole of moon, south pole of Earth. That analog between the 7th and 8th continents is very reassuring. A lot of lessons to be learned, and many other features at Malapert. Here again is illustrating the significance, what we think that galaxy first light imaging will mean, or potentially could mean, for the 21st century in terms of inspiration, motivation, direction. That the importance of the galaxy is manifest by the work we've been doing since almost the formation of ILOA, teaching about the galaxy and everything in it, and of course why the moon is so important, our first big step out into the galaxy. We have maintained a Galaxy Forum program even through the pandemic, much reduced, but still on track to expand soon. We've had 105 of these Galaxy Forums to date. We produced a galaxy map, useful to help one find one's way around. Very popular, and those are some of the locations that we've held these 105 Galaxy Forums. The Human Service Mission had some artwork that was never fully implemented to women on the moon, and we want to have some access to astronaut capabilities to service our robotic instruments up there. Maybe timeshare on an astronaut to calibrate the lunar observatories that we hope to start putting up there this year. And as I mentioned, ILOA and Space Age Publishing Company have been very consistent and in cooperation with Moon Village Association some years ago as well, and continuing to advance the first woman on the moon, which former Administrator Bridenstine, as you remember, said would be incredible, and I think it would. Why shouldn't the landing of the first women on the moon in the 21st century be as significant as the landing of the first men on the moon in the 20th century? Why astronomy from the moon? And speaking to John Menken's request for science, there's the case. There are some observations that are feasible only by using the moon. You don't have to go all the way out to L2, as magnificent as that mission is, to get a radio-free environment and look at deep space from the far side of the moon, using the moon itself as a shield from Earth, from radio frequency. The stability of the moon provides a very large, stable platform for interferometry with very long baselines, including possibly Earth-Moon baseline interferometry. The atmosphere or exosphere of the moon, extremely thin, almost non-existent, as we all know, which is excellent for many astrophysical observations. And it's interesting to know that the exosphere of the moon is even thinner than Leo. And then one doesn't go to the moon just to do astronomy, but once one gets to the moon, I believe observation in astronomy will be one of the first and widespread activities, and access to servicing and upgrading will be much easier than space observatories. So our observatories, as small as they are, will be serviceable from the beginning. This is a graphic that Madhu Thengavalu may be very familiar with, because it came from his book that he co-authored with Dave Schrunk and Bert Sharp and Bonnie Cooper, and Madhu, showing basically that the moon will likely see a global placement of telescopes and observatories.
I remember very well, Steve, and that was done by Bert Sharp.
Thank you, Madhu. Well, special credit to Bert Sharp and you all for publishing it. It's one of my favorite images, showing the ubiquitous placement of telescopes. And why not? Just like on Earth, wherever people gather, they look up. So I'm coming up to time here and probably should move along. Just some snapshots. Our former ILOA Emeritus Director, Commander John Young, was the pioneer of astronomy from the moon with that far UV spectrograph on the left, that gold anodized instrument. And it's still there. You can see it behind John and the flag there. So tribute there. We mentioned China and India has aspirations. We've had discussions, not recently, but we hope to resume them with the new director, Somanath, regarding India astronomy from the moon. Professor Rao was our longtime and very effective director and responsible, I believe, for Chandrayaan being the first to aim for the south pole of the moon with the landing. It didn't make it, but more power to them on the next flight. Japan has 2 missions to the moon this year, including iSpace, which should be following hopefully a successful Intuitive Machines and Astrobotic mission earlier in the year. In South Korea, an orbiter later. There's interest in astronomy from the moon in South Korea and really worldwide, wherever one looks. So that's my update, and really appreciate the opportunity to share our enthusiasm with yours, and look forward to more of the same. Aloha from California here, but you're always welcome to give a call or stop by, let us know when you're on Hawaii, and love to see you and let you know what we're up to. Love Mauna Kea. Thank you very much, and aloha. Thank you, John and Madhu.
Thank you, Stephen. That's great. I have a question for you. It concerns current events. There was an announcement just a few days ago of a prospective Chinese orbiting telescope. This was announced in IEEE Spectrum, and I was just curious if you'd seen the article. It has to do with I'm looking at the article now. It suggested the launch of some 9 radio observatories, which would then take advantage of the shielding on the lunar far side, and rather than putting the radio telescope on the surface, would do the radio observations from orbit. I wanted to see, one, did you notice this when it came out a week ago? And what do you think about orbiting observatories rather than surface?
Well, our mission is to touch the moon, to operate from the moon, and I think the potential long range to build 100-meter, 1,000-meter observatories on the moon is significant, given the 1/6 gravity. As far as lunar orbiting telescopes, I briefly saw that reference in the IEEE and didn't go into the detail. Doesn't surprise me, all of the innovation that's coming out of the China space program, that they're looking at that. And thank you, John, for pointing me to that again. I do want to look further into it. I know one of the astronomers that's going up on the first mission, on Intuitive Machines mission with us this year, Jack Burns, is a longtime advocate of far side astronomy, including orbital far side astronomy. So I think it does have promise, as well as limitations. It's great to see that innovation, and interesting you bring up.
I've just posted the link, the IEEE Spectrum, to that article in the meeting chat. If you want to just get it directly, because that way you don't have to look it up. Also, one other question, if I may. have you paid much attention to the creation within the International Academy of Astronautics last month of a permanent committee on the subject of lunar far side radio observatories and interference?
Mhm. I have not. I've been working more with the IAU, the International Astronomical Union, on those matters, but worth taking a look at. Right now, we're go ahead.
I was just going to say they were soliciting prospective members, and it just seems to me that this is very much in your bailiwick, and the creation of this permanent committee is quite a new thing. And it might be something that you would be interested in.
Well, thank you again, John. If there's a link you could send for that, that would be great too, but I'll follow up on IAA matters. So thanks a lot. What is the name of it again? The IAA committee?
So it's the IAA has formed a permanent committee on the subject of essentially radio astronomy from the moon and potential issues with interference in radio astronomy. Give me just 1 second, and I'll see if I can't find that for you.
I know that there's been a long time concern about far side radio quiet, and there have been efforts. I believe Claudio Marconi.
Claudio Marconi, thank you so much for reminding me. Claudio Marconi is in fact the chair of the new permanent committee.
Well, that makes sense. It's a long time and growing concern. I don't know. It'd be interesting to see how that China projection of orbiting radio telescopes would impact a radio quiet far side.
Yeah, I had exactly the same thought. That a quick win, but maybe one that produces some radio noise that is challenging to deal with. Dallas Bienhoff.
Yeah, I think you're right, pointing to that the far side as being another area for where Moon Village Association can step into and mediate and coordinate, because it's a contested use area like other South Pole locations.
So it's another area where there may be another area where there may be interest in from the GEXLA, the global group on sustainable lunar exploration that the MVA created last year. That might be an opportunity for them. Gary, I saw you posted a number of things.
Yes,
in the chat for everyone.
This is the information on the NASA coordination efforts with respect to comms in the lunar region with international partners. The existing regulations with respect to radio astronomy on the moon and the shielded zone of the moon that was agreed to. That was the latest and greatest, along with the draft LunarNet interoperability specification. And this is all current stuff.
Thank you, Gary. Dallas, you've been waiting patiently. You had your hand up. Dallas, you're on mute. Dallas Bienhoff, are you there?
I'm having some technical problem here.
John, while we are waiting, maybe Steve knows something about the MVA first payload for a camera on the moon. And does that have any kind of connections with what you're doing, Steve?
Well, not immediately, but Giuseppe and I have talked about that. We know about the first technical mission, and your technical director from Egypt. I can't recall his name. So I've talked with Giuseppe briefly about the not so much the payload as the destination share, I believe, in Malapert Mountain, and we could very much use some collaboration in that direction. I think it's I'm really surprised that it hasn't been spoken for, so to speak, by NASA or CNSA in particular, and ILOA speaks for it, and I hope that MVA, along with its payload development, also looks at the destination for that payload, which would deliver that long duration Earth observation that we both are after.
Yep.
I
I want to be respectful of everyone's time. I know we've run over a little bit. Dallas, did you manage to get back online? You're still on mute.
I did. It came back up. Sorry for the interruption. I wanted to mention to Steve that Maston is now advertising for a primary customer for their second mission to the moon on their CLIPS vehicle. So that may be a way for you to get to Malapert, Steve.
Well, thank you, Dallas. We've had earlier discussions with Maston briefly, and do consider them, and thanks for that refresher.
Yeah,
maybe
and
worth.
Good to see you, Steve.
Yeah, same. Well, so many of you. It's great to get see you on screen, or your name, and hear your voice, Dallas. Good to see everybody again. Thanks a lot for this opportunity.
Okay,
and
thank you.
all the best.
Thank you, Steve. And let me just say thanks to all of you who have hung with us. I think we lost. I think we've lost Inatani Sensei, although he might still be online. Okay, but at any event, let me go ahead and wish everybody a good remainder of your Wednesday. And we will see many of you again tomorrow morning. Tomorrow is our third and final day for the workshop, and we will begin with our third and final keynote from Madhu Thangavalu, bright and early at a little after 5 a.m. at Pacific time.
See you then, John and everybody. Thank you all for yet another wonderful session, the second day of the MVA architecture program. Thank you all.
Okay, very good. See you all tomorrow. Take care. Bye-bye.
Take care.